let's do some more investigation into the Goonies. So last time we were looking at how the name tables get populated. And let's look at that again to refresh our memory here. So there was a table of pointers, I think, so at 5F40, which is inside the ROM, there is a pointer table. So E600, E880, EB00, these guys all point to encoded, I assume, name table data. So if you go look at E600, that should, I think, be the first room of the first stage. Right, so it's all 5E and 5F now. Wait, did I go to the correct location? Yeah, E600 should be correct. So this shouldn't change when I load the game. Is the controller working? Yes. Okay, so stage 1. Yeah, so this data doesn't change. And I mean, I was confused about all the 5F and 5Es up here, but that's of course the top wall part of the thing here, of the first stage. So question is this encoded or not? Because it doesn't look too encoded, as in these aren't apparently being like run length encoded or anything else. So I guess we can try to change these and see if we see any changes straight in oh wait, no, E600 is not in the ROM, right? So this might already be the decoded data, right? Because if we do modify this, I don't know if 0 is the best option here. And we go back. I mean, it might get overwritten now because I'm reloading the first stage. Yeah, of course it does. That's fine. At least we know where the data is that is being overwritten, right? So let's put a watch point on E600. Well, I can do it via my button here. And then we'll reset and have the first stage loaded again, so we can look again at that function that does the decoding of this data. Okay, stage 1, and now it should break, which it does at A3D8, right? That was an LDIR, meaning that that would be part of the, that's a block copy, right? So that would be part of the decoding, I'm assuming. So let's see where it's coming from. So HL2DL for a length of 7 in BC, right? That's only 7 bytes. That's quite low, and it's also not a rounded number, so to say. It's not 8 bytes, it's only 1. That's also a bit weird. But let's look. It comes from E1F1, so that's a little bit higher up here. Yeah, so perhaps this is where it's being decoded, but why would they copy this thing like a little bit further down here at E600? Unless, I mean, surely you can decode that straight into the pointer, right? Into E600. They, for some reason, see the need to decode it here. What was it? E1F1. Yeah, so these guys here. Because the LDIR instruction already ran once, right? So we're pointing at the second byte here. Also, another question, why do they only copy 7 bytes when clearly they have to copy like 32 bytes here, right? 8888. Why wouldn't they copy the entire thing at the same time? Okay, it's 8 bytes though. Yeah, because it already ran once. Yeah, so it's copying 8 bytes at a time. So it starts with 5E and starts with 5F, so that's literally the same thing 4 times. Why would they do that? Okay, I mean, it doesn't matter, I guess. So it pops and it continues, right? And it returns. So there's a jump here, a for loop jump to A3CF, which is the start here. Okay, E1CA we have to look at. Because we are writing the E into something, E1CA, okay, that's right here. So that's F0. Okay, let's do this from the top though. So this is the start of the for loop. I'm assuming that, yeah, our function is going to start a little bit higher up here. Probably here. Okay, so let's try stopping there. Oh no, there's an unconditional jump here, right? So it's probably, we'll see around here as well. These are relative jumps, also unconditional though. A3CC, that jumps here. So maybe this call is also a target point where we can jump to. That's a bit weird. Okay, let's reload. Okay, so it is breaking often in here, but that's fine. Let's just reset. It's going to break a bit, that's fine. Okay, let's load stage 1. Where do we start? At the XOR, yeah, just after the unconditional jump, so that's not part of it, I'm assuming. Unless we do jump here, A3BB. Let's see if that is jumped to from somewhere else, or called, I guess. A3BB. Yeah, it's being called here, at least. Yeah, it's literally called. Okay, so that's the start of the function. Good. So everything above here is not part of it. Okay. And let's see at the call side here if there's something we can figure out. I mean, 0408 is being hard-coded, loaded. It is calling a different function with M. Well, that's also weird. Is that a thing? Yeah, I haven't seen that before. Yeah, so I'm assuming that the accumulator does indeed contain an input, although we're immediately XORing it though, so we're setting it to 0. So actually we're clearing it out. And then there's a relative jump to A3CC, so we're immediately stopping or skipping this entire part. So we might jump into here as well. So A3BE is probably jumped to or called to as well. Yeah, it's being jumped to. So that makes it a bit hard to figure out like the flow of the thing, right? Because they're using jumps and calls and they're like intermixing stuff here. But fine, we're jumping immediately to A3CC after putting the accumulator on 0 by XORing it out. So that's, I mean, pretty much nothing happens then. Okay, so the first thing we're gonna do is call this function. Yeah, so we can ignore this one as well, even though it's the call side. So A3BB, if we need to figure out something higher up, we have this call side here, the only call side. So 59FF does not appear in the stack though. That's also quite curious. Oh no, 5A02, you know, it's the point after, right? So that's the first thing on the stack. That's on top of there. Of course, that appears in the thing in the stack too, because that's where we actually came from, right? So the one of interest is 0408 here. 0408, I mean, it's in BC, right? So that's usually used for counters and stuff. Let me get the calculator. It looks like to be a high number though, so I'm not sure exactly what that's going to be. But let's look anyway. 408 in hex. Oh, 1032 bytes. That's just over a kilobyte. That might be something interesting as well. Let's see. So yeah, let's get back to, well, we're in the start of the function here, right? So what do we have as incoming pointers here? We have HL is 2 and DE is E1F0. Let's see what that contains. E1F0 is indeed our start of our working area, but that's not the target where we're going to write to, because that was E600, which still contains the old data because I just did a soft refresh, right? I didn't do a hard refresh. I assume this is going to be unpopulated when I actually reset the console, and actually I'm curious enough to do that. So let's take this one off, and yeah, we have one breakpoint left where we need to look. Can we do a hard reset here? So E600 is, I'm assuming, empty. Wait, oh, it's still, okay, it was still paused. My mistake. Okay, so let's do it again to be certain. So E6, yeah, it says F zeros at boot, of course. And I'm assuming this doesn't get overwritten as soon as we hit the breakpoint. Yes, exactly. So that's still virgin memory, as so to say. But we are writing it at E1F0, right? Yeah, so the DE is E1F0, and curiously, that already contains a decoded chunk of the first room. So we're actually already too late when it comes to decoding the level data here, right? Because apparently it was written here already. So I don't know why this is separate, as this. I'm still not clear on why this copy is happening instead of writing that immediately into E600 here. I'm going to walk through it and see whether it copies 8 by 8, like chunks of 8 bytes, or not. Let's see. So yeah, we're loading DE, so that's the pointer where we came from, right? Into E1CA, that's a little bit down, or a little bit up here. That's going to be around here in this one. So we're loading that. Oh no, we do load the entire pointer. Okay, so we're loading the pointer to our start position, maybe for some indexing reasons, perhaps. I'm not sure exactly why. Let's see. So we're pushing some stuff, that's fine. Oh, so... Oh, I missed the fact that this call put E600 in the first... in HL here. I assume that the call did that, because that wasn't the case, right? Which would make sense. 45DA, let's see what that does. That is, yeah. So if you see this is usually, I mean, I'm assuming this is going to be indexing into that original array that we mentioned, right? The array at where the base pointer to the room name tables are at 5F40. It's going to index in that based on the room number, and I'm assuming then that this XOR A, that puts 0 in the accumulator, right? So I'm assuming that it's going to use that as the index to fetch, maybe. Well, I mean, we have another call here, so that's a bit tough to track. For 607. Yeah, we're doubling A. Yeah, I mean, that's pretty much the first thing we do here. Yeah, we're loading the A base pointer. Well, I don't know. 045FF, is that the max? No, nothing to do with that. So yeah, we're doubling the accumulator already immediately here. So yeah, I'm assuming that's going to be indexing into that array. Okay, we're loading B with 0. That's weird, because that's the count. Oh, maybe it's just set in the top thing, because it's using the BC register, right? Okay, we're doing that 8 times, fine. Exchanging the two target pointer and source pointer, that's fine. So we're copying from E1F0 to E600. That's indeed the first 8 bytes, right, for BC amount with our elder instructions. So the first 8 bytes are going to get copied into our area here. And then let's see. Okay, and then yep, that's what happened. And then we exchange again, that's fine. And then we're popping BC 0408. Sure. Popping HL. Oh, so we're going back to E600. Okay. We're loading C into A. That's the 8. That's the amount. And we're loading. Oh, and then we're loading the base pointer again, the one we saved here temporarily, into DE. Okay. We're calling 405B. That adds E to A. Okay, that's the bottom part of the pointer, right? The bottom 16, the bottom 8 bits. So F0 is added to 8. Okay. I mean, this is just okay, and it increases D, which is the top. So it's adding whatever is in A to the DE pointer. Okay. So now we're pointing to the next chunk here, this one, I guess, E1F8. Yep, so DE is now E1F8. And we're loading 20 hex. Oh, okay. So that's 16 times 2 is 32. But we don't have 32 bytes decoded though. That's interesting. And then we're calling 4056. What does that do? 4056. That's this one. Add L to A. So that's 20 hex, or like 32 added by E600. Oh, okay. So it's skipping a bit. Oh, so, okay. So it is doing something strange. So is it adding it here then? Are these the next ones? Maybe because if you look at the first room, there's like 4 layers of wall at the top and they are identical. So maybe they decode these 2 lines once and duplicate them twice, like copy them twice over into the target area here. Because we skipped 20 hex, so we're at E620 now. I'm assuming. Yes, so now E620 is our part, and we're jumping up again, A3CF. Yeah, and then we're loading the base pointer. Okay, let's do that. So we're loading the base pointer, the guy over here. E1F0, so that's this pointer. We're saving some stuff. We're loading a 0 in the top part, so 8. 8 is our counter, fine. And then we're swapping the pointers around. So now we're going to copy from E1F8, which is this part. But we're copying that in this guy here. That's a weird way of doing this. So, I mean, the difference is this one is 5E, F, E, F, E, F, E, F, and the other one starts with an F. So 5 F, E, F, E, F, E, F, E. So they're like swapped around. But then these 2 lines are identical. Very, very weird. So yeah, so this is going to get copied in this row here. Right? And then we're doing the thing all over again. So we're loading C into A, which is 8. We're loading our base pointer. Wait, E1CA, yeah, that's our base. Oh no, that got updated. Okay, so yeah, that got updated. So we're progressing into this thing. Okay. Right, so now we have progressed to E200. Okay, sure. Again, 32. So we're going 32 lower again. So now I'm assuming E640 is the target now. Yes. And we're pasting those 8 bytes. I mean, let's look at the width here. So we're populating these tiles here, right? So we have 32 columns. Okay, so we have 32 columns. These all represent one of these columns, right? So we have 16. Right, so these two are right below each other or on top of each other, right? Yeah, yeah. So this is the left side. Well, the first quarter, I guess, of the left side. Second quarter of the left side on the left side, and the first quarter of the right side, like quadrant 3 and then 4. So these are on top of each other. Okay. Like it's a bit strange that they have this entire routine. I wonder if it applies to all the other rooms as well, this specific logic. Okay, so I'm gonna go through here. We're copying this to E640. So yeah, we're alternating E, F, E, and presumably E660 gets one too. Okay, our pointer updates, again 32 or hex 20 bytes farther down. Oh, and so now we're jumping. Yeah, I was looking, so DJNZ checks the BC register to see whether it's enough, whether it has enough, if the for loop has exhausted, right? If the counter is finished, but it's on 0208. I mean, it is the entire register, right? Let me double check by looking at the opcode. Right, so oh no, this one. So DJNZ. Yeah, I was thinking of another opcode here, but it's just the B register that's decremented, and B is currently at 2, so it's not 0208. Like it's literally just 2. That's the counter of the thing. So it has to do that 2 times more. This is one of them. So 0660. Yep. Well, yeah, the copy happens here, and then 1 time more. Okay, we increment our pointer 32, and then we're at 1. Oh yeah, okay, so now it decrements, that's it. Okay, so it did it 4 times, right? Okay, so 1, 2, 3, 4. Okay. And we exit this function as well. Okay. Okay, so that's just a copy routine. So the watch point we put was in the target thing here, right? At E600. But that's, of course, not good enough because we need actually, well, we need to see what writes here, I assume. But it's still confusing. How the entire level data is built up, because it only got like four rows here, or like 4 columns of the screen. I mean, it's decoding 4 things. That's also inefficient because they could have only have had 2 and just copy them like that because they're identical, right? So they're doing that in chunks, I guess. So what I'm curious, is this going to get overwritten now, or is it going to write straight into this one? Because we have to do the other thing here too, right? We have the other 3 parts of the screen, the 3, so we only did the first column. If you divide them by 4, we only did the first one, right? So let's see. Right, so we have a loop here, which is still on 4, 5, 9, C5, so it jumps back. So I'm assuming this is going to do the same thing. Yeah, so we hit our thing here again, and now we're doing the 3 other ones. Okay, I assume. So let me hit the L there. Yeah, now it's doing the second column of 4, I guess, horizontally. Okay, so let me exit this function, because this is just a copy function, right? It's not super interesting. And I want to see where we end up again if we go out of this function. So the loop here, oh yeah, no, we return from this one as well. Okay, so this loop here, this one, does this 4 times. So the entire top gets filled in. So let's break after this loop, and it should all get filled in here. Yeah. Okay, so that's a routine to alternatively copy this pattern EF or FE to all these positions here, to the top row of the room. Okay, and our pointer here, yeah, that's still exactly the same. That's our source material. Okay, loading 4 into the accumulator. Okay. Okay, so we're still in a loop here. We're popping BC, so B is 14. 14x, I closed my calculator. I mean, it's 20, right? 16 plus 4. Yeah. So 20 times, we're doing something 20 times. How many? We had 23. Oh, yeah, but wait. I was going to say we have like 23 or 24 rows, but a couple of them are already used up, right? So if you look at the bottom here, we have 23, so that's 0 based. We have 24 rows, but 4 of them are already used up. 2 for the top here and 2 at the bottom. Yeah, because the line is part of this second to last row at the bottom. So we do have 20 lines in the center here where the room is made up of. And that's what we see here. So B is 14, and this loop loops over every line then. Okay, so let's see where we start this loop. 559C1, that's right here. Okay, let's continue the loop. So we're saving some stuff. We're loading 4 in the thing here in B. That's for this loop, I assume. And then, okay, what is in the 9dB6? That's something we haven't seen yet. 9dB6. I have to type that. Why is this brown? Oh, I have the wrong symbols loaded. I have to change that. These are the symbols for Eggerland. Yep. I have to load the Goonies symbol file. Okay, because we didn't know. Wait, what? It doesn't contain any symbols. That's impossible. Of course it does. Okay, that's nonsense. Do I have a typo that prevents it from parsing the symbols or something? Oh, is it because of this? Okay, it's a semicolon, right? I think it's confused by the first line being non-symbol like. Perhaps that's the reason. Nope. Okay, I'm going to I mean, I'm in the correct folder though. That's weird. I mean, that's gonna mess with our reverse engineering here, because I need that symbol file for sure. But fine for now, I guess. So what we were looking at, 9DB6 contains something interesting because we're loading that in the accumulator. 9DB6, which is in the ROM, I'm assuming, right? If we subtract 4K from that, yeah. And I'm assuming we've already progressed in this thing here a bit further down. So this might be encoded data for the rooms, perhaps. Let's see. Because, yeah, so DE is a pointer, right, like which can change. So I'm assuming we're already some way inside the data here. We can break on here later on. So I'm going to look at 59E7 here, if it's small or not. Oh, only one call site, that's good. It goes from here to here. Okay, I have to look at the call M thing though. I haven't seen the M register used. Call M. If the sign flag is set, it calls that address. So it's a call based on the sign flag. Okay, like it is a conditional call. Okay. Yeah, same with call E and stuff. I see. Call P. Okay. Okay, so it depends on the sign flag. Okay, so we're loading stuff, but we are also calling stuff here. So let's just see if we can see something happening if we call this thing here. So this is not going to change, right? This is just the 31 that we loaded into the accumulator. And the question is now, will something happen at 6E00? No, what was E600? Either here or perhaps up here. Let's see if we execute this function. Yes, okay. Oh, does it do 4 at a time here? That might be the case. Okay. And it already E3 4D. Yeah, it already copied the first one here, and the no, not the second one. Okay. And then exactly, so we are increasing this or incrementing the DE pointer. So we are reversing this array here. So I'm going to open a new window so we can look at 9DB6. Right, so that becomes the next one now. So this is definitely information that affects what gets copied from our temporary little buffer here to our target area where we store the data, right? Right, so we're loading 8. And we're going to the next one, which we do. Okay, so what's going to happen now? So is the next one going to be filled up now? And is this going to change? I'm assuming this one is going to get filled in now and immediately copied to this position here, perhaps. No, all 4 changed in our, so we're decoding like 4 sets of 8 bytes at the same time. Oh, did I overlook? Yeah, no. It's the same thing. I didn't see these guys here. Yeah. So it's doing not just this one. It's doing the plus 20 hex, plus 20 hex, plus 20 hex. So these are all separated by, so our temporary decoding thing is, they're all separated by 32 bytes, by 20 hex. So they're underneath each other. So we have E54D, right? That's the first one. And then we have zeros 20 hex bytes below that. Again, zeros, 20 hex bytes below that, and then C859EA. So we have E5, zeros, zeros, and C859EA. Okay. That does make sense. So they're always decoding 32 bytes and then putting them underneath each other on the screen. Then it basically comes down to figuring out what 59E7 does, because that's the one that decodes the data and puts this in this little temporary buffer of 4 sets of 8 bytes, right? Yeah. Yeah, the question is where does it fetch that information? And how does it decode it? So 59E7. Oh, that's this one. Okay, right. Okay, 59E7 is the one we're interested in, so that's this one. I'm going to restart because I want to see that from the start, from the get-go. So I'm going to take a screen. Well, yeah, it's the 5E5F alternating bytes, right? Yeah. And that's also the reason why they didn't make it more efficient by only storing one set of 5E5Fs, because they're doing like the 4 rows of the horizontally divided screen, right? Like, yeah. Okay, so let's restart the round here. I mean, that's going to break all the time now. That's fine. So yeah, we definitely have like 4 rows. If we look at the tile thing here, that's our 5F 5E thing here. If you look at the tiles. Yeah, these guys, that's 4 rows of it's 94, 95 in decimal, of course. That's 5E, 5F. And there's 4 rows for that, from 2, 3, 4, and 5. And then we have the stalactites and stuff. Yeah. All right. So this is the interesting one at, okay, that's all gone now. That's normal, that's fine. Let's reactivate the breakpoint. It's reloading, that's fine, that's perfect. So let's reload stage 1. And we break for the first time. And what's our pointers looking like? So the start here, we were looking at 9dB7. Apparently the start is B2. So that's the start. 1, 1, 1, 1. That also, I mean, it might make sense, because we're doing that 4 times, right? The first 4 rows. Well, no. If we have to look at 4 columns horizontally, they're all identical. So that also might mean something, right? And the question is, what does this 1 mean when it comes to where is the actual data, right? Is this what kind of instruction is this, right? So we have 9dB2 as an input. We have 4 as a counter, but that's maybe not relevant. Okay, so we're saving these guys. We're testing A for 0. So A contains 1 here. Would it be the round number? The room number, sorry. So I mean, I'm gonna change this to, if I can. No, it doesn't wanna. I have to. Well, no, I should though. Does it now load room 2? Yes. Well, at least the first 4 of the first column here. Yeah. And that makes sense, right? Because that is the top right of the next room. So we're in scene 1-1, and the top left of the next room where I'm going to go into now is that, I think. No, it's not. Oh, is it flip? Well, that's yeah, that's not possible, right? Where is that from? Yeah, it's water touching the floor here. I don't think that's in the next rooms, right? The next rooms don't have water, I think. Yeah, no, the next room doesn't have water. That's a bit weird, but fine. I mean, we're messing with these values here, so that's to be expected. Okay, let's reactivate our breakpoint and take a more in-depth look here instead of changing values. But the accumulator is definitely being tested here, right here. So it's not 0. We're ANDing it with 7F. That's the bottom 3 bits, I think. So 7F is, oh no, it is the bottom 7 bits. Okay, so we're extracting the bottom 7 bits from whatever is in the accumulator. So it's definitely not a round number. They are separating the top bit and the bottom 7 bits, apparently. Okay. So we're ANDing 1 with 7F. That remains 1, of course, right? And then we're loading 5B. Oh, that's interesting. That's a hard-coded pointer, and that's in the ROM, 5B65. So let's look at that. I'm going to open another one because we need all of them. As long as they don't dock, it's fine. 5B65. Okay. This looks interesting because you see level stuff here, right? If we compare that to how the round looks, how the pattern tables looks in memory. Okay, that's interesting. And we're immediately calling stuff. So I'm gonna first look at these functions in here. So 4607 called multiple times, many times. Okay, what does this do? Not much. It's doubling A and calling 4056. Okay, so it's doubling A, calling something, loading. Okay, so that's going to affect HL, and that's being loaded into DE. Wait, so loading H. Oh, no, it's getting a pointer, and it's getting the value of that pointer into DE, right? Because it's loading into E, it's incrementing and loading the next byte. Okay, so this looks up a pointer 4056, and it's the double of A. Okay. Oops. And that's again a little function here. Oh, we're indexing again, I guess, because we're adding L, which is our pointer, right, to A, and then loading A into L. So we're increasing or incrementing the HL pointer by whatever is in A. Is that correct? So we're only affecting L, meaning it's the bottom byte of the 16-bit pointer, right? And we're adding the accumulator to that. Oh, and then increasing H, right? So it's if it overflows, then it increments the top byte as well. That makes sense, right? Otherwise, you would have like you can't add a value across the boundary and not update the top part of the 16-bit pointer. Okay, so I'm correct here, right? So it adds the accumulator to HL. Okay, I'm going to write that down in the sim file. Oh yeah, my thing didn't work. Okay, so let's remove these guys to make sure that that's not an issue. Add A to HL. Yeah, I think that's what that does, right? That's so we're adding L to A, that's the same thing, of course. Then we're loading A into L, yeah, we're overwriting L with what we just added together. If it doesn't overflow, we return. If it does overflow, we increase the top thing. So that just adds A to HL. Okay. Let's see if I can load the symbols now. If I can't, I have to restart perhaps. Yeah, it was those things at the top, I think. Not this one, this one. Yeah, okay, that's better. Oh, okay, so yeah, that's of course handy because now we already immediately see what this function is. Good. Wait, was I looking at that one? Yeah, I was looking at that one even. Look up room name table pointer. Yeah, if we go back to this one, I should dump again though, so I don't. So I have my symbols in my text file here too. Yeah, we were looking at the first function here. Yeah. Okay, I should have loaded the symbols. Yes, so this doubles A, calls our add A to HL, and loads that into DE. Okay, so this might not be 100% correct though, because it depends on a value of A. Because it depends on HL here. So the name table pointer is based on 5B65, I think. Even though it's in the 9 area. Wait, no. Our name table pointer was in 5F40. So that could be around here. Wait, let's see what it does though. So this might be the wrong name for this function. Look up room name table function. Does call our function here, add A to HL, and loads that into DE. But that's not correct. This function simply doubles A and adds it to HL and puts it into DE. Yeah, that's what that does. And the fact that I'm saying room name tables here, that's not correct because HL is an input to this function. So where are we? Yeah, so 5B65. So we might be doing the same indexing in multiple arrays of the. There might be multiple arrays making up the level data, and so we might be doing the same indexing in that array, which is what we're doing. So not necessarily the room name table. So 5B65. That's this one here. That wasn't our pointer. So the other one was like with the E600, that stuff, right? And the reason why we are doubling here is because we're dealing with 16-bit pointers. So I'm assuming this is going to be 5C3D as a pointer. 5C3D. That's. I mean, the fact that there's 5 E's, well, that would be this one, OF here. So yeah, but that would mean that the doubling, I mean, the doubling is a wrong expression though. It's just, we're dealing with 16-bit pointers here. Wait, where am I? So add 8 to HL. Oh, no. So the pointer is correct. It's the name of the function that's incorrect. It's this one here. Let's put them in order and keep them in order. So add A to HL is fine, but this one isn't. So for 607, so we're starting with 5B65, and then I'm going to go into this one. And so A is 1. Go into this one. So we're doubling this. That becomes 2. because we're dealing with 16-bit pointers, so 2 bytes per pointer. And then we're adding that to our HL pointer, right? So that should become 5B67. Yep. And we're loading that into DE. Oh, no, the thing it's pointing to, right. Yeah. Okay, so that dereferences the pointer. So A is an index, and it dereferences the pointer that HL, of which HL is the base, right? The first element. How are we going to write that down? So this is definitely incorrect. So it's a get pointer function. Get pointer at index, I guess. It's getting the pointer at a certain index of a pointer array. It's not get index, right? It gets a pointer at index and into DE. That's what it does, right? So let's verify that. We started with what was it? 5B. I forgot the thing. 59F3 is where we came from. 59. Let's quickly look up the value again. The base value. 59F3. So we came from 5B65. That was the base thing that we gave the function 5B65. That's this one, but we are indexing, we got index 1, right? So it's these guys, 5C40. Yeah. Oh, so we're getting the point. Yeah, we're getting the pointer. So are we dereferencing? It's just getting the pointer at index, get pointer at index, right? Because it didn't read 5C40. It just got the pointer value, well, the pointer itself. Yeah, I mean, get pointer at index, that does make sense. Okay. Okay, so we return from this. Oh, and so that meant that we took the bottom 7 bits. We're still talking about the same accumulator that we loaded here, or that we received in this function here. And that was 1. So we're, I mean, we're testing for 0 here, but we're not doing a conditional whatever. So I don't know why exactly that's the case. But fine. So we're extracting the bottom 7 bits from that value, and we're using that as an index in the array that starts at 5B65. So that we're gonna name that one too. I don't know exactly what it is yet, but we can give it a name just like this one, right? Like the name table things, because this isn't 100% correct either yet. We don't know exactly what all these pointers mean, but 5B65 is something of interest that has to do with the level decoding at least. So how are we gonna call this? Level decoding unknown pointer array. Okay, and then we call 5A05 1 tiny second. Okay, we're calling 5A05. Okay, that's right here. Okay, that does quite a bit. Lots of comparisons. That seems to be operating on data. And that's good, because that's going to be our decoding routine. I'm assuming it runs to here if we don't jump out of it. Yeah, I see loops. Yeah, definitely many tests and conditional jumps, comparisons 10x, 20x, 30x, F0, and with F0, so we're extracting the top nibble. Yeah. Okay, so I guess we're gonna have to find out what this does. Also, it starts with a base pointer that's hard-coded, E1F0. I mean, I'm gonna have to get another. Oh no, E1F0 is our target area, right? Yeah. That was where we were decoding the value here. Yep, that's where the 4 lines or the 4 chunks of decoded data are going to go to. So in fact, I mean, I can write that down in the symbol file too, because that looks pretty obvious, and it's like literally hard-coded here, and I'm assuming that's the only place where we are writing there. Wait, we only have, yeah, we only have two references to that. In this one, we're loading it into HL, and in this one, we're loading it into DE. That's fine. Yeah, so E1F0 is, I mean, that's beyond everything here. E1F0, yeah. That's like a temporary decoding area for level, well, temporary area for level decoding, and that's 4 sets of 8 bytes that get copied vertically, right? Because it did four of them vertically, one underneath the other. Okay, so E1F0 is our target area. That's good. Okay. That should be, of course, I mean, again, that should be an array of like 32 bytes. That's why I have to do some work on generating sim files from like a JSON format that just specifies, okay, this is an array, the length is 32 bytes. Otherwise, I have to do this stupid stuff where I have to spell out the entire thing here. I mean, these are all sequential chunks of data. I mean, that's an array, right? I mean, I should be able to define that as an array, and I don't think that these basic sim files can do that. So like just similar thing here, that's an array of 3 bytes. I should be able to specify high score length is 3 and it starts at E055. But yeah, I still have to do that. Okay, E1F0 is the start here. Okay, we're loading immediately L into A and we're comparing with 10 hex. How is that ever gonna change if you load a hard-coded value into HL? So L is F0, right? Or is it the other one? Let's go in this function. Right, so we're loading that thing into HL, E1F0, and then we're loading L into A, which is F0 gets put into A. And then we're comparing that to 10. But how is that ever going to be different or have a different outcome? Because it's a hard-coded value that you just loaded into A. So if it's less than 16, which it of course isn't, we're jumping to 5A12. So what do we skip? We're jumping here. Then, okay, we're comparing H, then the top byte of the 16-bit pointer, comparing that with E2. I'm gonna jump to 5A4C. That's a bit farther down for C. Oh, and then we're just exiting the function. We're loading E1F0 and we're exiting the function. Okay. Oh, maybe, right, of course. Maybe we are jumping back up here from below. And that's, so we're probably affecting the HL pointer 4 times, right? We're doing the first chunk, then the second chunk, third, and then the fourth. So we're probably jumping up back to 5A08. And then this does make sense. This comparison, I mean. So do we jump up? Yeah, back here. Yeah, jump, here's a relative jump, of course. That does make sense. And we're doing that multiple times. Okay. So that's the top of the loop, so to say, because we have to do this 4 times. But we're starting at E1F0. Okay. So yeah, we're comparing that for some reason to 16. And what is E2? E2 is 226. That's a weird value for the top part. I mean, I guess it makes sense. Maybe we'll figure out, because it's going to have a different value based on where in the sequence we are for iterations, right? Okay, so let's not worry about that right now, because we are taking a jump to 5A12. We're not doing this stuff. We're jumping immediately here. Okay. So now we're loading DE into A. So DE points to 5C40. Did we know that? 5C40. Yeah, that was our dereferenced or our indexed pointer in our array. Okay. I mean, I should be writing this down though. I think this array starts here, and I think it might stop here, right? Because these don't make sense anymore. It's 1808. That's not going to be correct. Yeah, I think I'm gonna start copying this stuff over into a C++ file or a C file, so we can. Yep, I'm gonna put it on a desktop for now. Well, no, let's do this better. Good from the first go. Wait. Okay, give me a thing here. Let's go make a new thing here. And let's save our file here in the Goonies folder, source main CPP. Where's my, no, let's name that main CPP. Okay. And I'm not gonna make a CMake file yet. Okay, and I'm going to copy this data array because we're going to need that, right? And it starts here. Okay, let's get the hex editor so we can copy paste, because we unfortunately can't copy paste from this thing here. Okay, let's get the Goonies ROM. And let's search for this list of pointers. 3D, 5C, 4D, 5C, 48, 5C, 4E, that should be enough. Yep. Oh, no, I can't copy from this one either. I used hex dump, right. Fine. I mean, it sucks, but... Come on. Okay, so go to hex dump -c the Goonies ROM. And now we can copy more easily. Where's my VS Code? I'm gonna open that. Nope. Yes. Nope. ROMs. Goonies hex. Okay. And now we search again for 3D, 5C, 40, 5C, 48. Okay, that's the one here. And I think it runs all the way here. Okay, let's clean this up. And we started here. And it stops, I assume, here, because this is the point. This pointer would be 1808. That doesn't really make sense as a pointer. So now we just have to count how many there are. This is our pointer array. Okay, yes, you don't know about C standard ints, that's fine. Okay, I'm gonna change the value here. Okay, why are you complaining? Is it because of the number? I guess it's because of the number, right? So, why is this not... Oh, wait, why is this not formatting? Is it because of the error? That's weird. Okay, why is it not formatting though? Fine. I will calculate with the hex editor then, because I have to have the length for the standard array. I have to enter the exact length. Instead of just telling me, it says no, it's wrong. Fine. Like it could have told me here. Oh, from int to uint 8d. Why would that not be the case though? It's weird. So we're starting at, well, no, let's do the end first. It's this one. Let's go one farther because we're counting zero based, right? It's at the bottom, I think. The address is 1C48. And the start is, where was it? This one, 3D. Yeah. The start is 1B65. So we have a length of E3, 227. Is that correct? Maybe 226? Okay, it's not complaining about that anymore at least. Why is it not formatting? Right, it didn't load the C++ stuff, I guess. Okay, I'm going to... Okay, let's clean this up. I'm going to close this. And I'm going to copy these files in this folder. Okay, my thing is very slow. I don't know why. Every time I'm streaming, my Nautilus is super slow. So I'm guessing I have to... Yeah, let's move the sim file out of this as well. Why not? Okay. So we have the sim file, and I'm going to cheat now, and I'm going to look at the Eggerland project for my CMake file, because who wants to learn that by heart? Okay, let's copy that. And now I think if I load VS Code now, it's going to initialize the things. The C++ stuff. Let's see if it does. Yes, I trust the author. Okay, let's take GCC 13 here. Okay, that's better. And then this is the Goonies project. And then let's get some warnings and errors. And then source main, we don't have any of these guys. No sources given. Yes, there are. Does it have to be different? Yeah. Of course, that's incorrect. Oh, can't find. Why can you not find this? Source main CPP, why can you not find this? No source is given to target. Okay, but target source is Goonies private source main.cpp. Why? What is this nonsense? Also still not formatting though. Wait, no, I'm targeting source, I'm not including. Okay, I'm confused. Let me open the other thing. No, I want to open this one. Yeah, I mean, that can have the same name, so that's fine. Cannot find source file, source main CPP. I mean, it's literally right there. Am I overlooking something stupid here? Okay. Still an error, I don't understand. Why can't you find the source thingy? Maybe I should update. Okay. There's a space after source. Of course. Okay, now you're confused. Why are you still confused? Okay, what the... Did I not move? I moved it though. Okay, that's good. And then okay. Jeez. Okay. We have our executable. So no, do not. Of course, I hit create file. Again. And again, it still won't format. I don't know why. Do I need a... Yeah, I need a Yeah, wait, I need a thing. Well, what is it called? The client format thing. Right. That's better. Well, I mean, that's debatable, but okay. So we have our pointer array. Well, no, crap. I need to. That's not good. These aren't workable values, right? I need to swap them around. Crap, because that needs to be 5C 3D. I mean, I guess we can fudge that by doing something, but that's fine. Okay, never mind. I'm just trying to follow the logic here first. Okay, we'll open this one as well, and then we have to load the correct sim file again so we don't mess up here. So we'll remove this load symbol file, and we're not going in this folder anymore, but we're going to Goonies, this one. Okay, finally. Okay, so we can reference this pointer array. Let's do this, get pointer from pointer array. Let's do this. What is that, assert? I think it is, right? And now we need a return value, because I'm going to build that up. UN16 to return values, initialize to 0, and then we take, so let's say we have index 1, we need to return 5C40, right? So we need to, how are we indexing this? Times 4, does that make sense? So if we do 2, no, it's not. Well, yeah, it is. If we have index 2 that we want, then we do 2 times 4 is 8. 1, 2, 3, 4, 5, 6. No, it's not correct. It's index times 2. Yeah. So we have index 2, that becomes 4. 0, 1, 2, 3, 4. Yeah, okay, it's index times 2. Okay. Index times 2, and that becomes the bottom. So 1 times 2, 0, 1, 2, that's the bottom nibble, plus index times 2 plus 1, and we shift that left 8 times. So index 1 equals get pointer array from array index 1. Let's see if that works. No, we have a mistake here. What's the mistake? Oh, it doesn't find assert. What is the thing for assert? Is it C assert? Can't remember. Yeah, C assert, that should work. That may change, suggest parentheses around the +1 inside the thing. Oh yeah, okay, that makes sense. Still, conversion from int to uint16t. Right, okay, so let's just static cast that to a 16t then. Okay, no, I didn't want to run that like that. Let's do that in a separate window. Okay, 5C40, that's indeed index 1, right? That's 5C40. Okay, so that works. We have 5C40. Good. Okay. Where were we? Yeah, so we're loading the hard-coded value E1F0, and then we're doing something with that E1F0, basically the pointer here to our target area. No, that's this one. Yeah, here is where we are going to write out these bytes, right? But we're comparing stuff, presumably which one of the 4 we are in. But we skipped over that, never mind. So now we're loading DE into the accumulator. Okay, DE was 0.25C40. That's what we just figured out here. Yeah, 5C40 we fetched. And then we're loading what that points to into the accumulator, 5C40. That's this guy here. Okay. Okay, so 5C40 is just after... Oh, wait. So, yeah, I've copied a bit too much data because I thought it ran all the way here. But that's not the case, right? Wait, is it this one that I copied? Yes, I think so. Yeah, 3D 5C40. Yeah, that's our pointer array. But the first one, or the index 1, 5C40 already points within this array here. So that's too much information here. Yeah, it's this piece that's too much. 35E, 31, 5F, 35E, 31, 5F. Yeah, that part is going away. 1, 2, 3, 4, 5, 6, 7, 8. Too many. Okay. Let's see how many we have now. 219. Okay, fine. Okay, so we load that value into the accumulator, and we are extracting the top nibble, which is an 30, right? Well, the 3 in the 30 we extract. Okay, so we're loading that, we're extracting, that doesn't change it. And we're checking if it's 0. It is not, so we don't jump. We're comparing it to 16, so 10 hex. That is not beyond 0, so it subtracts 32 from or 10 hex from 30 hex, and see whether it crosses the 0 boundary. It doesn't do that because 30 is higher. 30 hex is higher than 10 hex, of course. Okay, then by 20, also not the case, and then by 30 the 0 flag might be set. Yeah. Okay, so okay, I already see what's going on here. So we have an information byte that contains, that's split between the top bit and the 7 bottom bits. What was it? Yeah, that's what we ended, right? Yeah. We have an information byte that contains 2 sets of information. One set is in the top bit and the rest in the bottom 7 bits. Oh no, it's a top nibble. Okay, it's a top nibble. So 4 I mean, it is a separation. And then we have the value byte, because remember we copied 5E, the copied byte, the target thing was 5E, 5F, 5E, 5F. And that's what you literally see here, right? Like these 5E and 5F bytes are right here. So we just have to figure out what this 30 means. Actually, it's going to be a count, I'm assuming, because yeah, we have so 30 hex. 30 hex is 48, and we have 32 bytes. So in our thing here, so let's see what it ends up with. So we're taking the jump here to 5A43. That's far away. Well, I mean relatively far. So I guess that's the handler for in case it's 30 hex or more, right? Also, it doesn't do much. It calls a function and then it cleans up and it jumps, oh wait, does the relative jump to 5A08, which is the top? Yeah, and then we're doing the next. Okay, so it's gonna do something with this next byte, I'm assuming. Okay, so we're pushing the E, we're calling 5A50. Let's look at that in the other file here. 5A50. Okay, that's longer than I assumed. It's this. Okay, and we incremented DE, I assume. Well, no, we pushed it. Yeah, we incremented it here. Did we hit that? So DE is still called, no, DE is still 5C40 because we're loading that in again here. Oh, we're incrementing it. Okay, so we're loading the first byte and the next byte, presumably. And then we're extracting the bottom. Okay, sure. So first of all, I'm going to need access to these bytes, for which I need to load or memory map the ROM file. So I'm going to copy the ROM file in here. Yeah, I don't know why my file manager is so slow whenever I'm streaming, but that's super weird. Okay, so I'm going to go with open MSX, ROMs. I'm going to copy the Goonies file and I'm going to name it just goonies.rom, so I don't have the space in it. Okay, so we have the ROM file. Now I'm going to again cheat and look at my other project, so I don't have to remember the memory mapping stuff. Yeah, we need the file size. And we're going to hard code the path now, that's fine. So we get the file system included. And we need to open the file and close it after memory mapping the file. Okay. Okay, read binary, can't open ROM file, that's not going to happen. And then ROM data is going to be, let's make it a global pointer now, for now. And ROM size. Where does that come from? Okay, that's the file size. Okay. Why? Okay, I didn't put a semicolon here. And then prot read is defined in this one, I think. All right, and then map fail, could not map, and we're closing the file. Actually, let's keep that out of our main. Okay, and so we have our ROM memory mapped, so we can access it more easily now. And now we are going to, okay, we have to subtract 4K though, because remember, these are offsets within the main memory of the machine, and that's the ROM is loaded at 4000 hex, so we have to take that into account. Yeah. Let's see, does that compile still? Okay, it does. And now we should be able to index ROM data and just read the ROM file. So the thing we did was, I'm going to go back, like we checked the top parts, the top nibble, and compared it to hex 10, 20, and 30, right? So pointer 1 equals, nope, I'm in the wrong thing here. So we get the first one, and then what we do is we loaded that value, right? So I mean, yeah, it's going to be ROM data at pointer 1 minus, well, yeah, let me automatically, there's always going to be 4000 too much, right? So let's do that, minus hex 4000. Oops. And let's see what that value is, if it's correct at least. What's wrong? Oh, is that too much? From index to uint16. Okay, I mean, I don't know what the suffix is for a uint16, but let's then fix it like this. That should do the trick. No, why doesn't it want? Is that too much for a 16-bit? No, surely not, right? Okay, fine. It's because of the temporary, I guess. That is fine. Do we even need this still? Of course we don't. Yeah, I don't know why that didn't work at in the first, like if we were on the same line, but fine. So we have to subtract 4000. That becomes then, yeah, 5C40 becomes then 1C40, right? So I'm assuming that's going to be like that in the ROM. Okay, so we have to check whether that value is correct. Where's my execution thingy here? Okay, that's not good. Oh, can get file sounds of Goonies.rom. Okay, oh yeah, that's in the build folder, right? Okay, that makes sense. It's one level up. Okay, hex 30 is what we saw. And the value was indeed hex 30, I think. Yes, okay, good. We're on track. We're loading the correct bytes. Are we already in the function here? I was looking here, right? I was looking in the dump here. 5A50 is what we jumped to. Right, so we're loading the first byte and increasing the pointer and then adding it, extracting the bottom. I'm not going to do the 30, 20, 10 thing yet. Well, I mean, where was that? Was that not here? Yeah, here it is. Because we're in the 30 case. Okay, so yeah, let's add that. Otherwise, we might get the wrong data when we continue with the thing, right? So current value is thing, and then top nibble equals current value and F0. So we're taking the top nibble and then we're checking whether that, if top nibble minus 30, what are these? That's an int. I'm going to be explicit here and I'm going to say this is a signed integer. Smaller or equal than 0, then we do our stuff here that we're gonna do, right? Otherwise, the 20 and the 10 we'll do later because that's gonna do something else. I assume. Yeah, is it gonna complain about signedness? Nope. Okay, that still works. Right. So that's this section, right? So we're subtracting 30, and if it's smaller or equal than 0, which it is, because 30 minus 30 hex is of course 0. Then we continue onwards. And now let's jump in 5A50, which is where the bulk of the thing happens. I'm going to jump in here as well. And then we're going to look here. So 5A50, we're loading the byte again and going to the next one. And we're extracting the bottom nibble, okay? We still have the top nibble in this variable accessible, of course. I'm going to start by making it unsigned. And that's current value and bottom nibble, okay. So we're ending with OF. We're checking if it's 0 and we're doing something else. 5B29 probably exiting. Yeah, okay, 5B29 is too far away. Now it doesn't matter. We're decreasing A. Okay, that's the value. Okay, so we are doing current value decrement. And whether that's 0, so okay, let's do if bottom nibble equals 0, do something. If current equals 0, do something. We don't know what yet. So jumping to 5B to E, that's also quite far. 5B to E, look, that's too far to scroll. So yeah, we're bailing out. And then we're decrementing again, okay. Okay. And then we're loading A into B. Okay, so we're setting aside A and we're loading so that's the value now. We're loading the value into the accumulator. So we just need to have that variable available, right? And we're loading that into C. So we're saving the two original bytes. Actually, this is decremented by 2 already, and we're saving that. Okay, so but we have that in our current value variable, and then we're loading the value. I'm gonna rename this though. This is the meta information. Why is this so complex? Meta information, and then we have our value, and that is now the next one, right? So pointer 1, no. No, I think I made a mistake. Well, current value was... Oh, it's this one plus 1. Okay, no, that's correct. So value is this one plus 1, right? This has to be, I mean, I have to do that differently because that has to loop for like all the values in that array. So I can't just do plus 1. Obviously, I need to actually increment the pointer value. Like the pointer 1 has to loop over the entire array, of course. Right. So we now have the value. That's the 5, whatever it is. Yeah, so the 5e. So we handled the first byte, the 30 hex, and now we're handling, or we're loading at least the 5e, which we're then going to copy in the little target area, because remember that was 5e, 5f, 5e, 5f, etc. So that's what we're probably doing now. Okay, so we're loading the next byte and we're saving that somewhere. That's fine. We have it in a variable here. That's in the value variable. And then we're loading 5A79. Okay. 5A79 hard-coded pointer. What could that be? 5A79. That's not far away here. 5A79. That's this one. Because we we were around here in this at the start, right? Well, we're not. So 5B65, 5F40. No, that's not in this area. Okay, 5B is also not in this area. Okay, so we have another random pointer for some reason. Oh, E5. That's the second byte though. That's a bit weird. Okay. So we're loading a hard-coded value 5A. That's the same for every room, it seems. Just the value E5. Oh no, we're indexing again. Right. Probably. Yeah, because we're loading what DE is pointing to and we're incrementing DE. So we're looping over this little thing here too. So that's apparently another array, I guess. So let's see what happens in between this though. So we're loading that pointer and then we're loading B into A. B contains, that's this value here. That's our meta information, I think. Yeah, we decremented that twice. That's the thing that got decremented here and here. We're loading back into B here, or into the accumulator, and we're doubling that 4 times. Okay. Times 2, times 2, that's times 8, right? 2 for 8, oh no, 16. 2 for 8, 16, that also might make sense. Okay, and then we're calling a function. Okay, so let's write that down. Now we are taking the meta value. Let's call this temp for now, equals meta times 2 times 2 times 2. 4 times, right? Yeah, 4 times. And then we're calling for a 5B. So first of all, let's see if our values still track. So we have meta equals this, and then we have value, and we have our temp thing here. Okay, what are we doing again here? Narrowing int. Yeah, I mean, what's the suffix for? I mean, that sucks though, but I have to do this. I can do this a different way too though, but just to get it to shut up, but I'm still not doing this. Why are you complaining still? Like, why would it complain about that? I mean, that's like the stupidest, silliest thing to do. I just need the bottom nibble. Why is that a problem? So meta is an 8-bit unsigned. And I'm ending with OF. Why would that not be? Why? Narrowing conversion of int unsigned car into meta. I mean, that's stupid. And that it doesn't have a problem with, and that's stupid. but fine. Yeah, meta and mask. Okay, sure. That's the dumbest thing ever, but sure. I'll have to fix that up later. Okay, so what do we get here? Meta is 2e. We have a value of 5e and a temporary of 2e0. That's not correct. I don't know. We double that. Okay, sure. So let's see if these values match up with what we have. Where are we now? Okay, so we're at the start of the function. Okay, so we're loading the first byte. That's hex 30. That doesn't change. We're increasing the e, so that we're pointing at the next byte. We're subtracting the bottom nibble. Yes, the bottom nibble. Wait, did I do that correctly? Yeah, bottom nibble. Oh wait, that is 0, right? Or is that from? No, that is 0. So we are jumping. Yeah, mistake. 5B29. Yeah. Of course, this is for 30 hex. This, of course, is 0, the bottom nibble. So this is not relevant yet. So we're jumping to 5B29. Okay, my mistake. We are taking this jump, and we are doing this. So wait, there's an unconditional jump here to 5B31. Okay, so we're doing something and jumping back up. So we're loading then the value that now points to the value byte, right? So that's this one here. I might have lost it. Yeah, probably did. Oh no, we're just on top of that table. That's this one here, the 5e. So the value we are going to write, we're loading that into C, incrementing A. Oh, right, because so we're loading 5e, saving that somewhere, and then we're incrementing that to 5f. I remember the value we were writing was 5e, 5f, 5e, 5f. So that might be a routine for alternating bytes or something. I mean, sure. So we're increasing that, and then I mean, now we have to keep track of two variables here of the 5e and the 5f. Would it be doing two values at the same time always? I guess that's it. I think it has like a lot of branches that do very specific things for very specific patterns. So I'm not sure exactly what. We're in the 5e, 5f branch now that does an alternating 5e, 5f thing, perhaps. And then for somewhere else in the room, it's going to be doing something completely different, I assume. So yeah, I mean, what we are doing here now is we are reloading ROM data pointer 1 plus 1, and then we have like auto value 1 equals this, and then value 2 equals value 1 plus 1, right? That's in principle what's happening. Okay, so let's do that in this instance too. Also, where did we return? That's also important to know. 5B31. That's definitely not where we were. This is a big function though. 5B31 is right here, and we return. Okay, we are looping though. Okay, so then we do that. Okay, so let's move on. So we took the jump. We're loading in that 5e byte again. Yeah, that's 5e in the accumulator. We're loading that. We're saving that into C. And then we're increasing to 5f, fine. And then we're jumping to 5b31, which does the following. B gets, okay, B is 4, and I already know why it's 4, right? We're going to copy 5e, 5f 4 times. So we have 8 bytes in total of 5e, 5f, 5e, 5f, etc. Right? So we're doing something 4 times. we're loading C, that was value 1, into where HL is pointing to. HL is pointing to E1F0. That's our target area, right? So we need a target area. Let's give ourselves a buffer. Let's give ourselves, no, let's give enough. That's way too much, but so that's our output buffer. And now we can write into that, right? So we don't have to have E1F0. Of course, we'll just start at 0. We might need an index though. So let's give that, we'll start at 0. Because we're going to keep writing and keep continuing to write in that buffer, of course. So we're doing the writing here. We're doing that 4 times. We're loading C, so that would have been, it's one of these two, so I can't remember which one it is, but that doesn't really matter. Increasing, loading the other one, and increasing, and then doing that 5B33 4 times. Okay. Output buffer index equals value 2. I might have to swap them around if we see that's incorrect, but that's fine. And then value 1, and we increase again. Okay, so we've written 8 bytes already. Let's see if that makes sense. Also, we're going to have to get a function to dump our buffer, and that means I'm going to have to make this buffer global, which is fine for now. So we are going to just do this with a space. So we're outputting the byte, and the byte is in output buffer I. And then if I plus 1, oops, this might not be correct. We'll have to see modulo 16 equals 0. Then we are outputting a new line. And let's do a space at 8. Okay. So we did do this. This is not correct yet because we were in this thing. This is going to work, right? And then I'm going to dump the output buffer, and let's see if that compiles and runs. It doesn't, of course it doesn't. Again with narrowing shit. Conversion from int to the value type in a thing. Why is the value? Okay, sure. Okay. Have to be explicit, I guess. Okay, so we have 5f. No, that's visible. Actually, let me increase the size here if I find that quickly. Profile stream, text. Where is the font size? Oh, here. Okay, I didn't see that. Okay, that's a bit bigger now. So yeah, we outputted this 5F5E. That might be inverted though. So let's double check. And the inversion would be in value 2 or value 1 here. They might have to be swapped around. I'm not exactly sure. So let's just run it, right? We don't have to think, just run the thing. We're going to be writing here. and we're doing that 4 times. So we're loading 5e first. What did I have first? Of course, the inverse, but sure, no big deal. So this becomes 1 and this becomes 2. Okay, now we have the first 8 bytes written, and these are actually the name table bytes, right? So we are actually having the makeup or the markup of our first room here. I'm going to break after the loop of 4 so that everything gets put here. Yep, so that's exactly the same, and we return from this function. Okay. Okay, that means we have to separate this into a different function too. Decode room data, and we're gonna give that some parameters, right? Some like we need the index for this one here. So I'm assuming this is going to be room index. Okay, we can actually figure that out. So we have 219 bytes, right? That's an odd number, so that's incorrect. Surely, because it's 16-bit pointers, right? So that's probably one too many or something. So we have 219 over 2 equals, so 109 pointers. That's too much. So I was going to say that's not the amount of rooms, right? It's not. There's not 109 rooms in the game, so it's probably split up a bit more. So yeah, we can't make that assumption here. Okay, so let's just get the pointer index. I can index that with a size t, right? Yeah. Yeah, size t. And then we'll get this in this function here. And we'll do that for the first pointer, and then we return here after the loop. Okay. Wait. We're returning to this part though. Yeah. So we'll have to extract this to a function too, I guess, which is what we're doing here, what we're seeing in the code as well, right? So remember these comparisons, 20, 10, 20, 30, that happened in the parent function, right? So this is the case for the 30 hex, but that still happened in the actually it was this, right? Yeah, I think this was the function. Yeah, because the if bottom nibble equals 0, so the ending with OF happened. No, we need to go up from here. 5B to 9. So we're coming from here. Yeah. The ending from with OF and checking whether it's 0 happens in the function, in the parent function. Yeah, that's this. So this is a function in and of itself. Wait, how come there's no 5B29 goes here? It does a relative jump to 5B. Okay, so yeah, this loads the 2 first bytes and then jumps to 5B31. And then, oh, and there's a difference function that does the same thing, I guess. With a, yeah, this is just a for loop that writes out. Okay. Right. So yeah, we can either do this or we can do this. So there's an okay. The difference is a decrement. Okay. Yeah, that's interesting. So we have either an increment or a decrement in, because that's the only difference, right? So we're loading the byte in both sections. We're storing it into C, and either we increment or decrement. So yeah. That's like one thing here. So that is dependent on what? Oh no, we're just jumping here. I mean, I would have preferred to see that defined in the data itself, but yeah, apparently not. Yeah, that's a bit So where does that increment happen? Yeah, that's this one. No, is it? Wait, so we're loading the value of DE. Oh, no. Oh, yeah, no, that's the 5E, 5F thing. Right. Okay, so we can go the other way too. Oh, I see. Right. So, yeah. In case you have like 5E and 5D, if you go the other direction. Okay. Yeah, it's this +1 that can be a -1 too then, in some cases. Okay, so we don't return here, that's fine. After this one, we just continue execution, which is what we're doing here as well, right? So we're returning after this writing out of the of this part of this if clause. So we should end up back at this bottom nibble check, if I'm not mistaken. Let's see. So we called 5A50. Wait, was 5A50 where we checked the... So 5A50 is being returned from... Oh, yeah, we're extracting the bottom nibble here, so that's this part. So we are exiting the entire thing here, because we jumped outside of 5A50, which is this entire part. Okay, so what are we doing now? So 5C41 is our DE pointer, which is our current index in that thing. Okay. So are we keeping track of this pointer somewhere? I don't think we are yet. Yeah, that's this one. That's the one I mentioned that we have to keep track of separately as well. Because we're reading the first byte, the first metabyte, and then the value byte. Yeah, so this index just gets manipulated here, right? So we're incrementing that twice here. Wait, oh no, wait, we're popping a value into DE though. Wait. Okay, no, the base pointer. Okay, so we're going back to the base pointer and then incrementing twice. I mean, sure, I guess. I guess we're just not going to increment that in our code. Considering it's always going to increment twice, we can ignore that, I think. Well, yeah, because whatever we do with this pointer, with this index at least, we are popping the start. Oh, that might be different for different functions though. Well, we'll have to see, but yeah. I guess for now we can just increment and don't think about it too much. I'm assuming it's always going to be 2 though. Like you have 35E, 31, 5F, which is then the same thing but with starting with 5F, or the other one. Again, yeah, and when we come at this point, then we're doing something else. So these first 8 bytes define the first 4 rows of the top left part of the screen. If you divide the screen in 4 columns, it's the first column, the first 4 rows, right, are defined in these bytes. And this 30 and 31 thing, that's the meta information that says us something about the value bytes. Okay, so next time we'll see, or next iteration, we will see what the 31 does differently when it comes to 30. Oh, that's going to be the decrement, yes. Because the 30 does 5e 5f 5e 5f for 8 times, and then in the next line we had 5f 5e, so we have to do 5f minus 1 5e and do that like 8 times. So that's what this one will probably mean. Okay. But I'm going to assume now that we just traverse this array 1 byte at a time and that it will work out. So I'm going to get a value that keeps track of the index, and that would be that's the level data index, right? Because this is the level data we're dealing with. That's pretty much confirmed now. And let's start at 0. And well, no, let's start at pointer 1. Actually, I don't know if we need the pointer 1 value still, but actually let's also give that a uint16 thing, because that can't overflow. And now we can just do level data index plus plus. Yeah, so this is an index in the ROM data, but that's actually a pointer to the first element in that thing. So actually we're indexing this thing. So if we say it like this, auto level data, or explicitly type this thing, at pointer level data equals ROM data at pointer 1. Does that make sense? Oh, it's the address of ROM data 1, right? It's this, right? Yeah. And then level data index is starting at 0, right? Because now we're going to index level data with level data index plus plus, and this becomes level data as well. I think that should work too, right? And I know this pointer 1 becomes level data plus plus. We're already going to increment it for the next iteration. So now I'm doing this so we can reason better about these variable names, right? So that still works. Right, so now we have our level data is starting here at, well, not this one, but well, you know, the other one here, right? This one here. Yeah, so we have 5C40, so this guy here. That's where we are. Actually, let me write that down in the sim file. So 5C40, was it 5C40? No, yeah, 5C40 is level data room 1. Stage 1, no, it's, what was it called? Scene 1. Wait, and what is 5F40 then? Oh, that's the target areas. Okay, those are, yeah, that's the targets of each room, right? That's where the name tables reside in memory, right. And so they're like interleaving functions here and data. That's like in Eggerland, it was all separated, I think, or mostly. Well, maybe not all, but yeah. So we have this one. So the unknown pointer array, that's actually level data pointers, right? Yeah, that's the array that contains all the pointers to the level data, I'm pretty sure. Let's load our symbols again. No, not that one. Oh, it's here. Okay. So yeah, now we have the level data pointer array, 5C40. I don't know what the first pointer 5C3D. Oh, right, 5C3D is already part of it too, right. Oh, right. So I think we've included that in our table too. That's why it's an odd number. That doesn't make sense, or it didn't make sense, but now that's the reason why. So at the end here, we have some extra, we have a level data pointer as well, I think. So the first one points to 5C3D, which is here. So OF02 shouldn't be in there either. Yeah, this has to go. So we removed 3. I mean, it's still, well, 216 now, right? So if we say 216 over 2, that becomes 108 pointers. Surely there's not 108 rooms. So the rooms might still be separated by section in some way. I don't know, not sure. But we'll figure it out. Okay, so let's see what happens next. So yeah, we're increasing our pointers here, or incrementing, and then we're jumping to 5A08 again. Let's first see where that is. 5A08 is right here. Okay. So yeah, that's the area where we were starting to write, right? So we've already done these 8 bytes, and now we should point to the next one. Or no, we were doing 4 rows, right? We were filling up. No, that was down here. That was down here. We're not there yet. Okay. Yeah, we're decoding the next 8 bytes simply. Sure. So, but we end up here, and now HL should point to this one here, which is indeed E1F9. It points to E1F8, but we might increment still. No, oh no, wait. Yeah, no, E1F8. Sure, I clicked wrong. No, E1F8 is correct. So now we're pointing. The output index is now pointing here, and we also have that variable, right? So actually, this is not output. This is not the output buffer. This is the temp buffer, right? The temp buffer that does these 4 sets of 8 bytes. This is not yet the output buffer. So so this is actually the temp buffer, because later on these values will get copied into the output buffer, and we then need those separately. So this is also limited in size. I mean, even though there are lots of zeros here, I think we're only going to use 4 sets of 8, so 32 bytes. That might change in the future though. But for now, let's limit it to 32. And then what we also will have, I mean, I shouldn't have changed it. Well, yeah, fine, doesn't matter. We'll get an output buffer as well that we will fill in later, when we start copying from the temp buffer in a specific pattern to the output buffer. Because I'm thinking that's going to be always the same, like the 4 rows that are on top of each other. Okay, so we have written the first 8, and now we're going to progress to the next 8. So yeah, we're pointing to this one. We're loading L into A. L is F8. That contains E1F8. Oh, so basically we're checking. So 16. So it's checking whether it is around this area, right? Because wait, let me do it here. So we're loading L into A and comparing it with 10, which is 16. 10 hex, 16 decimal. Oh, wait, we're loading L into A, but A is F8. That's such a high number. How could that ever be less than 10 though, or less than 16. Like if you were to compare the, like what I'm assuming that they're trying to do is to see whether they have to do some different behavior, whether they are in the second column here or in the first column. But why? I mean, that number is always going to be super high though. So we're comparing to 10 for some reason. And we're jumping. Did we take the jump before 2? 5, 8, 12. Let's see. Okay, so we're skipping. Okay, yeah, we did that we did that last time too. So same thing. We were skipping right here. And then we're loading DE and taking the top nibble. That's the exact same thing. We're taking the top nibble F0 and we're checking against hex 30 again, right? We're ending with F0. Oh, is that already here? If the top nibble, right? So if top nibble, we forgot about that, equals 0, we also do something. That's this check here, which we don't hit. Okay, so we're loading DE. DE points to 5C42. 5C42 we still have, right? 5C42 is our current index. Yes, that we still have. So we do that. That's this guy here. Yep. Oh, but we're looping. We're not looping here. So I guess we have to do a limited loop, because I don't know how many times we're going to do that. Unless one of these jumps is the escape. Were we doing this 4 times? It might be the case though. So we jump back to back up to 5A08, right? Yeah, I think it was this one. This is an unconditional jump though. So there's no exit, there's no for loop here. This is an unconditional jump, so we can't escape here. So we must be escaping elsewhere. So either it's going to be one of these jumps, then I guess 5, 8, 12. So we have jumps all over the place here. Okay, so one of these conditions. So we only did this condition, whether it was hex 30 or less, or bigger than hex 30, I mean. One of these other conditions is going to give us an exit, a way out of this thing. So it is an infinite while loop, I guess, unless one of the conditions matches. I'm going to, instead of doing an infinite while loop, I'm going to get a counter. So we only do that like a maximum amount of times. Oh no, I'm going to call it while counter. I'm going to start at 0 and I'm going to say while counter less than 3, because I don't want to do an infinite loop yet, because we don't have the exit condition yet, right? We don't know what exits from this function. Might be this one, might be one of these other comparison functions, but yeah. So we're loading L and comparing this. I don't understand, doesn't matter. We jump to 5A12. We're loading the byte. That's the meta byte again, and we're ending with F0. In other words, we extract the top nibble. That's this and this. We jump. I mean, it's going to be the exact same thing, because we have hex 31 now. That we're loading is the 31 is here, right? 31.5F. So the only thing that's different between the first two and the second two is the 1 in 31. So let's see where that difference pops up. So we are going to do this jump at 5A43, I assume. Let's see. So we're loading the byte, taking the top nibble, checking whether it's 0. It's not. That's not the case. That's not the case. This is the case. CP compare with 30. Yes. So we jump to 5A43. and that's the same routine as we had here. That's this part. Oops. That's this part. So we load, we immediately call 5A50. Okay, sure. Let's go in. Right, because when we come back, we jump back up, right, unconditionally. That's the end of this loop here, right? Yeah, of the while loop. Okay, so let's go in here. Okay, then we load the value. We load the value. Go into the next one, that's fine. We're taking the bottom nibble, that's this. Taking the bottom nibble. Okay, we're doing an unconditional. We're testing the bottom nibble for we're testing the bottom nibble for 0. If it, now it is not, because it's 31. Right. Now we're here, and I'm going to simplify this because this is the only difference is going to be this plus becomes A1. I'm pretty sure. So this is going to be the same routine. So now we don't jump. We decrement A. A contains that bottom nibble. Okay, sure. We decrement it and we jump to 5B to E. Okay, so we decrement the bottom nibble for some reason and jump to 5B to E. And that's going to be that other section that does the decrement instead of the increment, I'm assuming. 5B to E. So let's continue here. Yeah, so before we jumped here, and we loaded the value, stored it in C, incremented, jumped over this little section, and then did the four times for loop, right? And now we're loading the value, storing it in C, and decrementing it. So it's just the same thing. Okay, so we can simplify this. Also, why did we need to decrement the bottom nibble though? The bottom nibble is in A. Is that relevant? No, because where we end up, we immediately overwrite A. That's simply not necessary then. So we have a delta, right? We have, where is the delta added? It's this delta here. Okay, so let's make that an int at delta, and I'm going to initialize to 0. Well, equals bottom nibble equals 0. If that's the case, then it's +1. Otherwise, it's -1. And then we're just going to do this, and then plus delta. Okay, so that's those two options combined, because that's all it does. That's pretty clear. I'm going to do it 2 times, so 0 and 1, yes. And what we should see is now the other array, or like this, the second set of 8 bytes. Okay, again, messing with this nonsense. Like these are all, I mean, sure, I guess it can, it's assuming it can overflow, but it's not going to. Would this suffice? Yes. Okay, so now we have, so we started with 5E and then 5F, so EF, 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 and now we have 5F, EF, EF, so the inverse, right? The other way around. Yep, that does make sense. And it is pretty much accurate, or the same as it will be in the game when we let this run. So I'm going to, I mean, it's going to be the same. So I'm going to indeed break after the for loop. And we're going to look at this here, and this is going to be 5FE, FE, etc. So I'm going to run. Yep, 5FE, and that's the exact same thing as we have here. So that's the second thing. And assuming the data is going to be again 30, 31. Where are we? Yeah, here, 30 FE, 31 5F. that's the exact same thing. So yeah, I can actually do this 4 times instead of 2. And we'll see that the first set is correct. So I'm gonna do this 4 times. Okay, and that, well, maybe, yeah, it's 30, 31. Yeah, it should be the same though. So I'm going to let it run and it should immediately do the next one, right? Because the breakpoint is just after this right thing. Yeah, it's 5E at the start twice. Okay, good. Now what happens is, I don't know, well, now we are going to copy these into the output buffer down here, right, at E600. Here, this dummy data is going to get overwritten by this. So we're going to copy the first one in the first row, and then the second one, a 20 hex after that. That should be a simple loop as well, I'm assuming, but let's see where we end up. Okay, so we're returning from our call. We should jump back up. Yeah, so we are now back again at this point here. And we're loading in the next byte, which is, so we did all these, is now we're handling 0818 here. That's our next data. Okay, loading L into A. Okay, we're again checking. Oh no, wait. Yeah, we skipped that check, right? L in. Okay, so now L is E210. Does that make sense? E210. That's the first one here. Okay. Oh, and now it is okay. it's checking for this this 10 here, so it stops after 4 sections of 8 bytes, I guess. Because now it does make sense that we're subtracting or comparing with 10 hex, but that's because it's E210 where it ends up, and now it knows it has to stop, right, or write out or whatever. Yeah, so now we don't make this jump. So we are going to write out this data, I'm assuming now. Okay, so we're loading H into A. That's E2. Okay, comparing with E2, sure. I mean, yeah. And that is the case. And we're jumping to 5A4C. I mean, we're doing some other stuff here. 5A12, did we jump? Yeah, no, we jumped here. 5A12. I don't know if that can fail here ever, because it's always going to be in the E2 range here, or maybe not, because this is one at E1 F0. Not sure, but that doesn't really matter now. Okay, so 5A4C. Let's look at it in the big screen here. 5A4C. I don't think. Oh wait. Oh, we're loading the base pointer and we're returning. So we're done with this function. Okay. So we're loading the base pointer E1 F0, the base pointer of where we just wrote 32 bytes, and we are returning. Okay, so this function simply decodes 32 bytes and bails. Okay. Okay, and yeah. So yeah, this we have to ignore. I mean, I'm gonna remove it. It's just to not make a mistake, because we only handled the 30 case. So there might be other cases will be up once we encounter other bytes, and the next one is going to be different, right? The 0810 or whatever it was. Yeah, but this is a little function that not does the room data decoding. It decodes the first 32 bytes. Or actually decode the temp buffer. It decodes the temp buffer data. Yeah, and I'm assuming we're gonna have to give this a function parameter that points to, that's this guy, right? The level data index, or the level data pointer, I guess, where we currently are. That means that if I'm going to extract that to a function, we need to access that pointer index globally though. Yeah, I think I mean, it's not the best code here, but that doesn't really matter. So we're going to set level data here, and also level data index. That's a local variable though. Wait, no, we need to. Oh yeah, no. That we need to have that globally because we need to progress through the entire level. Sure. So where this level data get indexed, get incremented here, that's fine too. That can happen in the function because once we process a byte, that's done. But then this belongs to a different function. Wait, why did I stop when it was 4 though? It might be this part only though. Yeah, because yeah, I think so. So this is a function. And then this uses the level data index and increments it. That's why it's global. Yeah, we're loading a byte, and then wait, do we have to do that 4 times? Yes, we do, right? Yeah, this is always done 4 times. So this is not a while loop. This is simply the buffer decoding of the buffer thing happens 4 times. Okay, let me rename this one. Oh, that doesn't even used, but that's fine. Yeah, so we did have an exit. It only happens 4 times. It might be happening different amount of times next later on, but that's we'll encounter that, or we'll handle that when we encounter that later. That's fine. So yeah, we're doing that 4 times, and then yeah, because now after this we have to write out the buffer into the temp buffer into the output buffer. Yeah. So 5A05 is decode temp buffer, level data temp buffer or something like that. 5A05. Okay, that decodes the level data temp buffer. All right, because that starts here. Okay, so that function, the rest of this function, decoding function, only does this then. So we're having a conditional call here based on one of the flags. Can't remember which one it was. And then we're loading 0408 into BC and calling something else. Okay, and then we do return though, so there's no loop that comes back here. That's a bit weird. So maybe this gets called for every temp buffer then, because we need to process the next set of level data, of course, right? So okay, but let's first see what 5B3A does, and that's, I mean, it's gonna write out a thing in the temp buffer, I'm assuming. 5B3A. that runs until here, unless we jump out. I don't see any jumps outside. 5B48, that's a loop. Okay, sure. So let's implement this. We're loading 7. 7 hex. Okay, so we're popping AF. I think A, so A is the, yeah, so that's this push here. We ended that, so A was, well, A is changed a lot, of course, because we called like multiple functions. But A was the thing that came into this function, the parameter, the attribute of, or the function parameter for this function, I'm assuming, and that was 1. I assumed it was the room number, like the scene number, but it wasn't, because when I changed it, it only changed the top 4 lines, which is exactly what we're seeing, right? So I'm thinking this is the pointer index. Yeah, of course, because we're indexing into this thing. Yeah. So, right, it does make sense. It's this index. It's the index in our array of 16-bit pointers here. Okay, so how many do we have here? And now I'm gonna count now. Wait. So if we look here in the tile viewer, so we have 20 rows for the game board, and we're doing 4 at a time, so we have 5 sections, right? And then we have 4 columns, so we have 20 sets of pointers. Is that correct? So what if we then divide? 108 is not divisible by 20 though. I mean, 100 would make it 5. Where does the next pointer point to? That's also interesting to know. So we have our, not this one. Okay, that's a function. So that's the level data for scene 1. That's the function. I have to look again because I lost the number. Yeah, I'm looking for this guy here. That's called, yeah, this one, 5B65. 5B65, yeah, this guy here. So, I mean, yeah, that's also still a mystery what the first pointer is, because we started at 1, right? Not at 0, but at 1. So 5C40 we did, and then the next one is 5C48. Okay, that's simply 8 bytes farther down. So yeah, so 5C40 is this one, and that was handled by the first pointer, and the next is going to be read from this array, and that's going to be this guy here. So that chunk is indeed only these 8 bytes. So the first pointer, or pointer 1, points to the first 8 bytes, and then pointer 2, 0 based, points to the next, and this is right here. Okay, I guess they might be reusing stuff here too if this pointer thing changes too. So this level data pointer array might just be for stage 1, not for the entire game, because we have a limited amount here, right? So we have 216 bytes between the start of the array and the actual data, where the data starts. The data starts at 5C3D, I assume. Right, so the last pointer is 5F03. Wait, no, that's not possible. Because 03 wouldn't make sense, right? Would it? This might be the last. So I might be off by 2 here too. Well, the last would be 5EFD. Well, no, it does. Oh, right. This might be compressed too. Right. So the chunks might not all be 8 bytes long. Yeah, the compressed version of them. In other words, these guys here might not always be 8 bytes long. There might be, so now if you go to from 5C40 to 5C48, yeah, then we go to 5C4E, which is shorter than 8 bytes, right? 5C4E. So if we do 5C4E minus 5C48, that's only 6 bytes, right? So this guy, 5C48, only points to 6 bytes, right? So we can't like do a division and figure out how many chunks there are, because these are pointing to compressed chunks of data, not 8 bytes all the time. I guess the alternating 5E, 5F, 5EIF is only compressible in 2 bytes, right? Or like in these 8 bytes, I guess. That's like the worst case compression rate, I guess. Okay, let's see. Okay, so we're not calling this function. That's good to know as well, because I was gonna decode that function, because that's where we are, right? Yeah, 5B3A is not being called, so we have to figure out what the flag is here, because that might be called for other chunks. But fine, we can skip that for now. And that skip happens here. Okay, so the next thing is going to be this call here then. So we're loading BC with 0408. That might be a counter, not sure. Okay, load that, and then we call A3BB. Only one call site. And we immediately start by knopping out or removing A, or setting A to 0. So that's fine. I think it runs here. Then we jump out. Oh, we're doing LDIRs. That's good. So yeah, this is going to be the block copying thing that copies the bytes in the correct rows. And I'm assuming, well, yeah, there's no condition here. This is always going to be the same routine. And I don't think we have to reverse engineer that, because we know what it does. It copies the first 8 bytes to that position, and then the next 8 bytes underneath that. Yeah, it's like the four rows vertically on top of each other. But I mean, we'll have a look though. Oh, it does jump on, wait, it does jump on condition A3CC. Okay, so yeah, sure. So this part is like based on where we enter the function, which is always A3BB though, so fine, I guess. So the function continues here until we return. So we're calling something. Right, we saw this. This is the storing the current pointer we have, and then yeah, I think I'm just gonna write this, because this does an LDIR and then loads back up that pointer. And then DJ and Z, meaning it looks at B, which is being loaded with 04 here, right? Because the B register isn't being touched. Yeah, we're pushing it away and we're popping it after the LDIR. We need the B register for the LDIR instruction, so we have to push on the stack and pop from the stack. So when we pop here, it becomes 0408 again, BC. Okay, and 08, meaning C is 8 here. Okay, and that's the offset then. Okay, sure. So this is the repeat time. We have to do it 4 times, and it's going to be 8 bytes, I assume. Yeah, because we load C into A, and then yeah, I'm not sure. Well, that might be for 405B here, though. Not sure what 405B is. So I need to return to A3BB. Okay, that's fine. 405B. What does that do? Okay, we looked at this. We should give this a name too. So this puts E into A and loads A into E. I don't know, it adds E to A and then puts it back into E. So we're incrementing E with A. And then, okay, yeah, we're adding A to the pointer in DE. Yeah, I think that's what happens, right? Yeah, we're adding E to A, but then we're putting A back into E. And if it overflows, if it doesn't overflow, we return. And if it overflows, we increment the D as well. So I think that's just add A to DE. 405B. Add A to DE. Yeah, that's going to be, it's going to be 4056 is going to be just above that. Yeah, that's this one. Yeah, we have two similar functions here, and they do the exact same thing, add to HL and add to DE. Also, I'm going to re-export my thing here. So we're going to go into A3BB. Oh, next room to load. We already know this. So I need to re-export though. I exported my disassembly without my symbols, and that's going to change things here as well. If I look at this, yeah. Now we have a better thing here. Of course, it doesn't put the names at the top here. That sucks. But yeah. So we were at A3BB, right? So no. Yeah, this one here. So we immediately jump to A3CC, which is here, and then we're calling 45DA. Wait, did we not write down? Okay, I don't know, we're looking at these guys here. Yeah, we're adding, yeah, right. We had 408 in BC, right? That was hard coded. So 4 is going to be the loop counter for this for loop, the D, J, and Z here, and the A, the 8, which is in C, which is also pushed and popped here. So it become 08 again. That's being added, put into A, and then we are loading E1CA plus 8, right? Or the value that is in E1CA, which is our current pointer. So we're simply traversing the four parts of the temporary buffer. Okay, and then 32 is being added to HL, sure. Yeah, so this just writes it out. So if we look at that, we're going to take another look to make sure we are doing this correctly. But we have to look at this stuff here, right? So this is a source, and this is a target at E600, and we're going to copy this. So if we jump to A3CC, we're calling something. Oh, did that knob out? Wait, let me quickly look at 45DA, because I don't think I've looked at that yet. 45DA. Oh, that does stuff too, though. We do have to look at that, because that's... Yeah, I saw something change, but I don't know what it was. Because that does a lot here. That we're seeing lots of rotations and stuff. Yeah, that does something as well. But we're keeping track of DE, which is our start of our thing here, E1F0. So we're at the first one. We're going to write that here somewhere. Come on. Yeah, we wrote that there. So we keep track of that pointer. We're loading B with 0. Oh yeah, BC, right, that's the 0408 is now just 8 because we're copying 8 bytes. We're block copying 8 bytes to our first row here, right? Okay. And then, I mean, it sucks that the values are already there though, because I think they're going to get overwritten. we're exchanging, popping, loading C, right? So now we're going to add to increment the pointers, 32. So now we're going to add 32 to our pointer, so we should be at E620 now. To HL, yes, E620 right here. And we're doing the next loop. So all we have to do is put these sets of 832 bytes apart in our output buffer. Okay, I think that's all it is. So right, temp buffer to output. And I think we have to keep track where we are though. And that might be this pointer here. Well, I don't know yet, because I can't just do a 0. Like, I can't just start at 0, right? Because we need to like write other stuff in the next iteration. So we write the temp. I'm gonna find or get the offset as a parameter though, because we're gonna need it anyway. So we decode the temp buffer. I can't combine this in the decoding function because we have to skip this call potentially, right? Or not skip it, I mean. So we start to write it at 0, and then what we do is we do this 4 times. And then we're going to copy 8 bytes, so we're going to have to do that as well. And so we're going to do 32 times I. That's our offset, right? Our target in our output buffer is the offset plus 32 times I, and then plus J, and the source is going to be I times 8 plus J. Okay, so output buffer. Oh, right. Are we using output buffer index still? Yeah, because that's our offset to start, I guess. I'm assuming we're going to do that sequentially. I hope so, at least that the thing is being filled. Oh, no, we can't do it sequentially because we're adding 32 bytes each time. Like, yeah, we're doing chunks or we're doing things in chunks. So we can't keep track of an output buffer index. So output buffer offset plus, so that's our base offset plus I times 32, right? Because that's the outer loop, plus J equals our temp buffer, and that is going to be I times 8, because we have only 4 sections of 8 length, plus J. I think that's correct. And then we are going to dump the output buffer, which we're going to copy from this one. And then let's just output 265 bytes. Yeah. Yep. So we have our temp buffer here, and then we have our output buffer, the first 256 bytes, and we've copied that. So the first one comes from here, then 32 bytes farther on is the second one, which is this one, and then again the third one. Oops. And then the fourth one gets copied here. I think that's what's happening in game. We'll double check. It's going to be hard to see because it's the other data is already there, right? Why am I E600? Was it right? Yeah, so it's these guys. I mean, it sucks that there's already data here, and I can't hold my 0 down because it fails after a while. So well, never mind. So we're gonna write it here. I don't know why it blocks after a while. That sucks. So yeah, we've written the first line already, and now I'm going to continue, and it's gonna do this line, and this line. Okay. Let's continue here. Right, and I'm doing the next one now. Yep. And the third, and now the fourth. No. Okay, so yeah, that's 5E, 5F, 5E, 5F, and that's what we see in my output here too. 5E, F, E, F. Yep. Good. That was an easy one, I guess. So this was only the variant that did the OX30 routine of like this one, right? So what this 30 thing does is, so the 30 implies it's this routine, and the 30 or 31 implies plus or minus, right? So it's this routine is just alternating between the byte and either +1 or -1. That's all it does. Okay, so now we're going to encounter a different algorithm, I'm assuming, because our source data is now different. So we did 30FE, 31FF, 30FE, 31FF, and now we're doing 0818. So we're definitely not in the 30 handler, right? It's going to be a different number now. So let's see where we end up. Yeah, we're going to exit this for loop, exit this function, exit this function. Okay, we didn't give this a name, so we might as well. 59E7 was the start. Let's see, 59E7. Okay, so what does that do? That is like the decode. Yeah, that encapsulates handling one pointer of the array, so one chunk of the level decoding algorithm. Yeah, because it gets the bottom 7 bits. Okay, we have to see what we give this function, because the bottom 7 bits are used for A, and that is being used to get that's the index for the chunk array, for the pointer array, right? So we have to look at the byte that's being given to us here in this function, and I assume that also comes from somewhere in the ROM. And the bottom 7 bits determine which chunk we are loading. Yes. So this is decode level data pointer, I guess. Pointer chunk, I guess. One set of 4 rows. Actually, it is 8 by decodes chunk of 8x4 tiles of the current or of the current room. Well, yeah, current room, that's fine. So we're doing a chunk, and I think this gets the pointer index as the parameter. At least the bottom 7 bits will be used as the pointer index. So we might see that there's two algorithms or two functions that get called based on what gets passed to this function here. Yeah, that might be different. Okay, so we'll reload our symbols, and we're out of this function now. Okay, so it's the information is in DE, so we exactly know 9db2. I guess we already looked at that 9db2. Yeah, that's these guys here. 9db1, I guess it started. Well, well, that's B0 though. Okay, B0. What is the bottom 7 bits of B0 are 30. Wait. That doesn't really make sense. Because that's exactly what gets put into the accumulator, as in other words, as the parameter to this function. It started at, I'm assuming, 9db1, and it's, oh no, I haven't done the increase yet. No, it's, of course, it's 1, it's not B0, because I haven't executed this line yet. If I do the increment, now it goes to 9db3, yeah. So this was indeed 1. And the 1 implied, okay, so we take the bottom 7 bits of 1 is of course 1, and that was used as the index in the thing, right? And now we're adding 8. Like, because I'm looking at the next one, and the next one is also 1. That's not really possible, right? Oh, so it's going to be this one, I'm assuming. Because we have B0 is 1, 1, 1, 1, 1, etc. And then we have B1 and data, maybe, I don't know. So we're loading 8 in the accumulator. We're adding H. We don't know what HL contains though. So we have to look at this function in detail. Instead of in the middle, we have to get this to the start of it, I'm assuming. What is this? Oh, this might be data, because that doesn't make sense at all. So I'm assuming, yeah, it's going to start here. And we're loading 9d80, which is the first thing here. Okay. So this is an array that we need as well. Get pointer at index. I think I have to specify index of what though. Get pointer at index into DE. Oh no, that's a universal function, right? Yeah, and the array is 9d80, and yeah, that was a universal function, and it gets the pointer at index, which is A, I'm assuming, and then E061 is where we are currently in the room. So okay, right, yeah, that does make sense, I think. Okay, so we're going to be jumping up, right, because we have a for loop here to 59C5. That's right here. Okay, that's a bit lower than I expected, but sure. Okay, so we're adding 8 to HL. What is HL being set to? We're jumping to C5. So, not sure. Never mind. We'll pop over it for now. Okay, we're doing the next one. DE points to 9dB3 now. 9D. Which is also 1. So presumably it's the exact same thing, right? But that can't be the case. Well, yes, it can be, because yeah, of course it is. These 4 ones are the 4 columns on the screen. So we have the first column we've done, but they're all the same. If you remember the first round or the first scene, 0101 does have the wall at the top, and that's exactly the same. So instead of like, that's the same thing 4 times. Yeah. And then we're doing something different. So this 31 here is the first column, but the second row, so the second row of chunks, right? If there's so we have 20. So we have 5 chunks per column, and 4 per row, right? Because we have 20 lines, and we're doing 4 at a time, so we have 5 vertically and 4 horizontally, right. So we have 4 times the same thing. In other words, this guy here, right? This 5E, 5F gets copied into here, and then the next one, and then the next one, and also in this one and this one. Yeah. Because the top of the room is the exact same thing. Obviously, that's how these 4 ones work. So we can skip over that and just increment our output pointer destination thing. It only gets interesting when we encounter this here, this 31. That also means though that this pointer here, 9080, that we load at the start of this function, is actually the level data that points to that contains the indexes in this array. Where is my VS Code here? They have many levels of abstraction here. So yeah, this pointer array. Actually, I should not load this hard-coded. I should load this from the ROM instead of doing that. Yeah, that would be better. Yeah, I need to cast this to a 16-bit value straight from the ROM. And then subtracting 4000 though, but sure. So this index is what gets passed from here, right? That's those ones we were looking at. And that comes from this array. So what? Yeah, we still call this pointer array. So we can give this a name now too, right? So these are, I'm assuming, compressed pointers to compressed tile data. That would make sense, right? Yeah. Crazy names, but sure. And actually, we just have to store that address in a value, and we should access that from the ROM, not from a static array here, because we have the ROM accessible, right? So that's that shouldn't be a problem. So let's define that address. Compressed tile data pointer array offset, incredible name again, and that's the hard-coded value of course I forgot where that started. Is it this one here? Yeah, I call this level data point. That's also not level data pointer array. This is the compressed tile data pointer array, and that's at 5B65 minus 4000. That makes sense, right? Yeah. I guess I can make that const expr so it calculates that immediately. I mean, it should optimize that obviously automatically, but I guess we don't need this. We just need to... I also don't need the assert because the game is going to give me these values. The game works, so it can't overflow this buffer. It's never going to request a value that doesn't exist in the game, right? Unless we do some weird stuff, perhaps. So now we have to get that from ROM data. So we have to reinterpret that as a uint16, I assume, yes. And we have to go to the ROM data, add index compressed offset plus index times 2, because we have a 16-bit value. Is that correct? You have a pointer, I guess, that you need to... wait. Should I build up the pointer like I did like this? I guess that's the easiest, right? Wait. Let me reset here. The only thing that, yeah, the assert was above that. Yeah, no, I need to do simply ROM data at compressed plus index times 2. Yeah, it's as simple as that, right? That should be the... plus index times 2 plus 1, and that shifted over, and then we have our thing. So yeah, we don't need that array in the memory anymore because we can just read it from the thing. Don't crash. Yeah, so that doesn't crash, so that fetches the correct data. That's good. So we can get rid of this. Get pointer from pointer array. That's that actually should be renamed to get compressed style data pointer at index, right? Because we have to differentiate because we're going to include a different pointer now. The only thing I'm not certain about is the fact that this base pointer is at 9080, which is the hard-coded value here, and apparently we are quite deep into it. So there could be other screens that are also, like all the screens in the games, like the main menu and stuff, that are also encoded here. That is this data before round 1, because what we're literally looking at is stage or scene 1.1 of stage 1, and it's quite deep inside that pointer. So there must be other data after that or before that. So 9080 is also an interesting one. So that would be the level, I mean, could we call that level data? And those are no, those are the indexes for this. Yeah, I'm just gonna call it level data, and that is 9080. And wait, I might actually do do it correctly here. So we have fewer magic numbers. Yeah. Right, EO61 is being, yeah, that's the index into this array, and that's going to, so EO61 is a memory location that we now figured out. EO61, that is the, why is that 1 though? Oh no, we're indexing into DE. Wait. Get pointer at index into DE. Unless that's an a 16-bit value, is it? Because get pointer at index into DE adds. Wait, did I make a mistake here? Because we're oh yeah, into DE. Okay, but it indexes into HL and puts it into DE. That's confusing. Geez, like the complexity. So get pointer. Actually, it is this, right? HL index. Of course, I can't use brackets. Can I? Well, maybe I can do. Just because this highlights. No, that's because I haven't closed it yet. Get HL index or A, I guess. Yeah. HL into DE. It's that, right? Yeah. So we're indexing HL at index A in the accumulator, and we're saving it into DE. Jeez. Let's see if it that would make more sense, I think. Yeah. So now if you look at this, yeah. So HL is 9080, which is the array we're indexing at E061, and we are loading that into DE. And then we are using DE into A here, and then we're calling the decoding function. Okay. DE is 1 though, so how can we... So that this is what worries me, right? So the 9080, or what was it? 9080, yes, is too far away from the value we're actually handling. So we'll have to start over and start here and see. I mean, this is going to probably trigger for the main menu as well, but let's continue onwards to the stage 1, scene 1 though. I'm going to see if I have other breakpoints set. I only want 59 beat 2. Okay, so I'm going to continue. So that didn't hit, right? That didn't hit because the loop goes below that. Like this loop 59C5 jumped up here, right? So that might do all 20 chunks of a screen. Okay, so let's now reset and see. I mean, it might break for the main menu. We're not sure. Come on. No, it doesn't. So these aren't stored in this table at least. No, neither does this one. Okay, now we break, and what do we get? So we're loading 9080, that's this guy here, and the one we are interested in is this guy here, 9db2. So for some reason, oh wait, is this this happens to be B2 though. So this might be 2 arrays, right? So 9080 might be the offset after this array, or added to itself, and then we end up at 9db2. So the next one would be 9D, I guess, which would be all the way here somewhere. Yeah, this guy here. So would the first stage or scene 1.1 run until here? From this one, that could be the case though. Assuming they are all, well, no, because we only have 20 chunks. This might be stage 1, perhaps. I'm not sure. No, doesn't matter. Yeah, so we load 9080, and we are loading E061. Okay, important one. E061 contains 1 at this point. Okay, sure. So we're indexing. Wait, where are we? 9080. Is it 990 then? That gets fetched. So we're setting, or we're loading E061, which is 1, into the accumulator. Yes. Oh, we're decrementing. Okay. Okay, -1 equals 0, and that's the B2, right? So we're indexing. Oh, no, it's a pointer. It's 9db2. Oh, okay, sure, of course. It's so again we're doing we have a one based scene number, I'm assuming, or round or whatever it is. I figured out this is the next room to load, but this is also room index related, right? So this is a one based thing. So the first room, I guess. Yeah. I think I've seen this Vampire. Yeah. Is this? I think I read an article about a remake or something where they did music, where they changed out the music or something to a better version. But I haven't seen this yet. But of course I'm not gonna cheat and look at existing source code. Of course, that would make it a bit too easy. Like the fun is in decoding how it works, right? Yeah. But I will take a look. I will take a look at the link for sure. Yeah, that was recent. Oh, so this is older than that. Okay, sure. Yeah, but I will definitely take a look at the link for sure. Right, so this is a one-based index. So I'm assuming room 1. And then we are decrementing by 1 and indexing then, so that becomes B2. That's our B2 at 9D80. Yeah, that's this B2 here, or the pointer, 9db2, the entire pointer, right? Because we're getting the pointer into DE. Yeah, 9db2. So these are pointers, okay. And the first one would then be, so it would, okay. So B015 is also a pointer then, or maybe not. Well, not necessarily. 9E41, that would be this one here. That would be the next one then. Okay, sure. So 9db2, we're loading 2 into HL. That's probably 16-bit related. We're loading 14 hex into B. 14 hex is 20 decimal. 20, of course, we have 20 chunks, right? We have 5 vertically and 4 horizontally, so we have 20 chunks. 5 times 4 also makes sense. And are there 20? So the difference is between 9db2, well, no, that's the first one, and 9E41. 9E41 minus 9db2 is 8F, which is 143. That's odd. So that's definitely not that's not what I'm thinking it is. So yeah, no, maybe there's other information there too. Yeah, not sure about that. But fine. So we're doing something 20 times. We're putting that in the B register, which is used for loop counters, of course. We're pushing that away, and we're loading 4 because we are doing 4 horizontally first. Yep, that's what we're doing, and then we're loading these guys right. So our pointer array starts at 9D80, and that is a pointer to chunk indexes, right? To so 9D80. So level, I call this level data. Is that level data? I guess it is though. So that's going to be processed 20 times, right? 4 at a time. Yeah. So let's and so yeah, level data offset are 16-bit pointers. I I didn't give that a name yet. So 9080. That would be, yeah, this is, so again, this is wrong. This is not a level data pointer array. That is actually this, right? Because level data, so this array contains pointers to the 20 chunks that make up one room. So this is room, well, let's call this, it's for a specific room, right? So let's call this a room data pointer array. And what was 5b65? 5b65, those were the pointers to 5c40 was here. That's the level data for scene in, that's again the wrong name. I mean, it's getting complex with all these abstractions, right? So yeah, so this points to these guys here. These first four ones are indexes in this array. That's 5c40, and these are compressed chunks of like this is encoded tile data, right? Okay, let me write a little tree here. So we have our tile data, which is encoded, right? And then before that we have an array of pointers to tile data, right? That's at 5b65, yeah. And then before that we have actually two before that. We have 9080, which is level data, room, was it room data or level data that I gave it? Yeah, room data, right? So room data, which is at OX 9080. And then, no, pointers to, yeah, because it contains multiple rooms, right? So this is an array of pointers to room data, and then we have room data at first at or scene 1 at 9db2, right? And then 9db2 has indexes. Well, these are room data indexes into right, because that indexes into this array, and then the tile data encoded tile data, and the first is at or scene 01 at 5c40, yeah, 5c40. What do you mean, objects? So you say, no, in Konami they use objects to draw the player screen, but what we're seeing, I mean, they're simply, I'm not talking about the sprites here, right? What I'm looking at is in the tiles, what makes up the tiles, like the actual the background thing, right? The makeup of the level itself, of the room itself. So we're not loading sprites or anything. This is just we're filling up the name table actually, right? To put the patterns of the pattern table on the correct position of the screen. Yeah, I haven't looked at those guys. So the waterfall, that things that move, right? I don't know. I haven't looked at that yet, whether those are sprites or whatever. Yeah, I have to look at that yet. I've only started at room 1-1, which is pretty static, but yes, maybe, yeah, sure. I will definitely encounter that when we continue on with decoding of the thing. Yeah, I don't know exactly what you mean by objects though. Like, I mean, you can put sprites on the screen or you can put tiles on the screen. So I don't know exactly what you mean by object, but yeah. So the first one is at 5C40, I think it was. Yeah, 5C40. Okay, so that's our level of abstraction here. Oh, right, but that would be something in their logic, right? As in the Konami way of doing things, right? Yeah, I see. Well, I mean, the first game I did was Eggerland, right? So I haven't, and that was HAL Laboratories. That wasn't Konami. So this is the first Konami game I'm looking into. So yeah, I haven't looked at any others. So these patterns might be reoccurring, and also like the other Konami games I have, they do look alike, like the font and stuff. Like they do look alike quite a bit. Also the scoring and stuff. So I do assume that they reused quite a bit when they made new games, which is fine, of course. But yeah, I'm sure we'll encounter that. So what I'm going to do now is I'm going to access this pointer and then just draw the first 4 at the top. Oh yes, okay, so yeah, I mean Eggerland 2, I was planning on doing Eggerland 2 as well. I have done the same for Eggerland, for the first Eggerland, and I mean, I can indeed support other puzzles, like other levels. I can perfectly load other level data inside the ROM, like custom levels and stuff. Oh, I've never heard of Illusion City. That's a game I've never heard of. I have to check it out. Oh, but isn't Illusion City a new game that you're developing, or is it something from the 80s? Because I don't remember that. Because the name doesn't ring a bell. Not that I know all the games though. Okay, I don't know about that one. No. Oh, translations. Right. I mean, it is quite fun though. Like, especially if you can change these games and make them do what you want. Especially if it's the old games and stuff. Yeah, that's a very interesting topic for sure. Room data pointers. All right, so 9080, this is going to be room data array. Let's make the names a bit uniform, right? So room data array, and then 5B65 is tile data array, compressed data. Okay, compressed tile data array. And what else do we need? Right, so that's something we calculate. This is we calculate. So we need the 2 pointers, right? The pointers to the 2 arrays. So we have the room data array, and that indexes into the compressed tile data array. Okay. Let's also call these the same in the sim file, 9080. So that's a room data array. And then 90 or 5B65 is tile data array. Okay, that makes it a bit more uniform. Right, now we're going to do this 4 times, so we have to read the pointer first, though, because now, where am I actually starting here? Yeah, I was immediately decoding the root. Yeah, this one here, that has to be looked up. decode room data 1 gets the compressed dial data pointer at index. Yeah, that's fine. Yeah, but we need to load these guys from the room data array. Okay. Okay, so now we want to, yeah, which one do we want to load? Like 1 is the first pointer, I'm assuming. Yeah, that's the first pointer. So so load scene 01 equals index 1. I'm assuming it's as simple as that. So we'll have a function that right, because we have to call this function 4 times. Right. So this is not decode room data, this is decode tile data, right? That decodes it in the temp of, okay, so these 3 things have to be done 20 times. Okay, but let's start with 4 times. And then we need this is a value, this is not an index, right? This is a value. Well, that gets indexed in the next array, that's fine, but we load that from this guy, from a room data array. So we have to have a get room data function. So we do get, no, we have to do that before room data. So we have to have this variable, right? And that gets for this guy. Actually, it's 0, right? Because it's the first room. So actually, we can say, I mean, I'm going to put this in a num, but it's going to be, actually, no, let me, I'm going to define it simply as a number. Wait. What's the best way of doing this? Because we need to, I don't want to write 0 here. I mean, we need to, yeah, no, let me put it in the enum class, it's fine. That's going to be scenes. I can't start with a number, of course. 0101. And that is going to be 0. I'm just going to explicitly type it out, but also I'm going to have to move that outside. And then we will give the scene okay, so we're loading scene 0101, and yeah, that's the room data because that is the first pointer. I'm assuming one second. So get room data. That's not void, but sure. And that's the index into the array at room data array, right? So scene. Why don't you know to underlying? I don't know what the include for that is. Utility. Scene times 2, because it's a 16-bit pointer. Yes, it makes sense, right? So we're reading from the ROM at that array. We're reading the scene number. This is 0, so we're reading the first one. What do we have? We have a pointer. Yeah, that gives us a pointer, and then we have to subtract 4000, and we give that as the offset. Yeah, I mean, that's a pointer. Yeah, we'll return a pointer to the start of the, and then we just have to read the value and increment. Okay, sure. Because that's the ones, that's these ones, right? That's these ones we're trying to read. Yeah, these guys here, these 4 ones are we are trying to read. Okay. So we have our pointer. And then we will return ROM data. So the address of ROM data indexed at pointer minus, what was it called? A ROM mapping offset. I'm guessing that gives us our okay. So we're, yeah, I think that should give us the 4 fours. So we have the room data, and now let's keep an index. Room chunk index start at 0, which we're going to right, and then we just dereference room data at room chunk index, which we increment. Yeah, that should work, right? And we're doing that 4 times. The writing is going to be wrong though, because I'm writing this, yeah, this 0 is going to overwrite 4 times, but let's see if it doesn't crash at least. Okay, that's wrong. And we do crash. Sure. Let's see if our pointer is correct though. So the pointer for the scene is what? That should be 90B2. And that's completely wrong. Am I indexing the wrong? Yeah, of course I'm indexing the wrong array here. It's room data array, of course, not the compressed tile data array. Wait, why am I? What's going on? Okay, what's going on? Jeez. That's a lot of data. Why so much? Oh, am I... Okay, I must be looping somewhere. So the pointer is 9db2. That's at least correct. So we have our room data. We are doing this 4 times. Oh, I'm dumping the output buffer 4 times. I shouldn't do that. Well, I mean, I can. Let's just do it once at the end and skip the temp buffer. Yeah, so it's messing up for sure. So let's see if we get 4 ones. Because the room data, so the tile data pointer should be 4 ones, right? So that has to be correct. Let's see if that's correct. Auto tile data index equals this. Yeah, that is correct though. I don't know why it's messing up so much here though, because that's like literally 4 times the same thing. And even though we're writing the temp buffer to output position 0, which should be incremented like 30 or 8 bytes each time, that's a bug, but that should mean that it should have put the same data on the same 4 lines all the time, and it's writing garbage elsewhere. Like we're doing 4 times the same thing though. That's impossible. So we're incrementing some sort of index or pointer each time that we shouldn't be doing. So we're getting the data, okay. We're decoding the temp buffer. Okay. Okay, level data. That pointer is not being set correctly, I'm assuming then, level data. Well, no, we get the pointer. So the pointer should be the same thing every time too, right? Of course, that's not pointer 1 anymore, but that's fine. Yeah, 1C40 plus 4000, of course, that's 5C40. That's correct, right? 5C40. Yeah, that's this guys. So that should be the same thing, right? It's the correct 8 bytes every time. That's correct. Then we decode the temp buffer. Let's see what happens in there. So yeah, we access this 5C40. Oh, level data index has to be reset. Okay, sure. Yeah. Because we're only doing, of course. That's not being reset. Why do we need a global for that? I don't think we do though. Yeah, we don't need a global for that. That has to be local, right? Because this is 4 times. Wait, why are we doing this 4 times? Oh yeah, because it's 2 bytes per thing. Yeah, we have the that makes sense, right? Yeah, we have 8 bytes and wait, does it? Oh yeah. No, I'm not sure now, but let's first make that a local. level data index. I think, no, we're reading though. We're reading from the level data. Yeah, no, that definitely has to be a local for sure. Okay, we're still off though, because that should have been overwritten, but we're off by some. Okay, so we're writing out that wrong. We're incrementing something else. Oh, temp buffer index. That's not being reset either. It indeed isn't. Oh yeah, we use that for the size, but the temp buffer size we can deduce from the length, right? That's 32. That's always 32, so we don't need this. And this is 32. And then this becomes a local as well. Yes, okay. Now what we need to do is we need to offset this by 16 bytes. Or I don't know how many actually that we have to look at in the code. So this is this loop here. So we're doing this 4 times, right? So we're loading 4 in the B register, which is the counter register for 4 loops. And then, okay, we're loading the E, which is going to be 1. Yep, into A. We're decoding that and writing that to the thing. Fine. We're increasing DE. Yeah, that's the second 1. We're loading 8. Okay, okay. So, and this is where we add 8 bytes to the output buffer, I think. So we're adding 8 to H, which is 0, probably because we're at 0, 0 still. And we're loading 8, okay, into HL. We're popping the BC again, so 4 becomes 3, okay. Loading DE, and then that means now, so if you look at the output, where is it? E600. Of course, these are already overwritten, so I can't really see any difference. But that means that this function has another input, because it's not only decodes the level data pointer chunk, it also writes it to the output, I think. Right. But which can be implied by the decode verb too. Yeah, so this might take HL into account, perhaps, as the offset where it has to write. Because 1 is the index, the chunk index, the thing that's this guy, the room data index. But it also, I think it might use a HL for the target position, and that the next target would be then 8 bytes down, right? Which is this guy here, the 8th byte here, or index 8, I guess. So decode level data punker 59E7. Let's quickly see if that is used. 59E7. So loading 8 into the accumulator and adding that to H. I mean, it's going to end up in those guys though, like that's pretty clear. And it is a repeat, right? 5E. Yeah, I'm just going to do that. So we need to keep track of the current column and the current row of chunks. So we have 25 by 4. We have to keep track of that. I assume that that would be the best. So it's going to be as simple as renaming this to current. No, these are rows within the chunk. So yeah, we need to current row, because that's the that remains the same. So we're gonna comment that out for now. Current row, and that happens 4 times horizontally, and then we have a current column. And that happens 5 times. So we have 5 vertically. And then within that, we do a chunk, which is comprised of 4 wait, no, we want to do our rows first, right? Is that correct? No. We have to iterate columns. Columns are 4. No, there are 4 columns and 5 rows. 4 columns and 5 rows. And we're gonna skip, we're only gonna do the first row. So let's make that temporary row 0. I don't want to decode too much because I know that the first entire row, the first 4 columns of the first row is all the same. Those are those 4 ones, right? So our algorithm that we have finished will be able to take that, but probably not the next. That's why I'm commenting out the next rows. So what we need to do now is give this function decode tile data and offset on where to start writing that stuff. So decode tile data has this guy here. That has to be, I mean, I can give it an index, I can calculate it. So pointer index means actually tile data index, I guess. And then we have output buffer index, and then we start to write that at this position. And then of course, yeah, because we're adding 32 to this base offset, right? So that should work. If I simply call it with the next one with 8, yeah. So this is current. I mean, it's better to do it in X and Y though. So I don't have to think if the row is Y. I mean, what's the point of renaming that thing? This is easier to reason for me. So, okay, so Y. So now I can just index by going Y times 32, right? Y times 32 plus X times 8. Yeah, I think that's correct, right? So for an entire row, or if we go Y plus 1, that means we have to skip 32, right? 8, 8, 8, 8. And for the column itself, we skip 8. I think that's correct. Probably not. No, it is not, because it should be 4 ones, right? I mean, the fact that the indexing is correct because it should have filled in this entire thing here. That's correct. Like the first set, and then the second set at these guys, and then the second or the third set. So that's correct, but it's using the wrong values here. So what are we missing here? Oh, room chunk index. Wait. So tile data index equals 49. Wait, is it? No. So this should be 4 ones. No, we have to. This has to be outside here, right? Because yeah, we're loading the tile data index, and then yeah, the 4 ones are for and then the first one is for the entire chunk, right? I think that's better. Yep. Yeah, we only have to query them 4 times, right. So now we have the first, the top row of the thing. Very good. So what I'm going to do now is do all of it, which is going to be completely wrong. As you can see, because we are missing some decoding things here. So we did the case for OX30, but we have other stuff now. But at least we can decode the first or the top 4 chunks in the row. And now things are going to get different as soon as we encounter other room index or tile data indexes other than 1111, which we had. Yeah, so these guys here, we start with 1111, and then we have 3168. Maybe it's somewhere else that I was looking, but yeah, 9080, and then maybe these guys. Yeah, 90B2. Yeah, so we start here. These 4 ones is what we did, and now things are different when it's 3168 and stuff like that. Okay. So where are we in the code here? I don't know where exactly we are. We are pointing to 90B3. Okay, so that's the second one, B3, and that becomes B4. Okay, so now we're going to handle the third chunk. Okay, we loop, and now we point to 90B5. That's the 4th chunk of the top row. We put that out, and then we again load okay, so 90B5. Wait, what? 90B5 is being. Oh yeah. Now we do it. Okay, now we write it to the output. We increase to 90B6. Okay, so now now it's getting interesting again. Now it's 31, right? So we're loading. Okay, we're skipping our thing there too, and we're exiting doing another loop. We're doing this 4 times for the 4 rows. Oh no, we haven't looped yet. Okay, now we have. So now we're loading 9db6, which is 31. Let's see what happens now. So DE 9db6, that's 31. Okay, the 31 gets loaded into the accumulator. Okay, and now we're calling our function here. So, oops, I was going to run to this. Nah, that's the 31, right? Let's follow with the code along as well. So we did this with tile data index 31. Yeah. Okay, so that should just get that. That's not specific. That's not special, right? That's just the get in pointer 31. Okay, so let's do that. Yeah, that's this indexing here. Okay. Okay, and then we're going to decode that in the temp buffer, and that's where we will see the decoding happen again. Let's see if we have the correct number here. So we're pointing at 5BC8, so 31 into that array, The array is, of course, no, we're still here. That's not that one. It's the compressed dial data array at 5b65. So 5b65 plus 31 hex times 2, right? Yeah, because we're in, yeah, I think it's that 5bc7. Is that correct? Yeah, 5bc7 is correct because I see 5bc8 here, which would make sense, right? Because we have 16-bit values here, 5bc7. Yeah, so that's 5d. Okay, which is, yeah, that's what we see here too. 5d contains what? 5d. So we're not on the boundaries anymore, right? So this is a bit weird, but sure. Because, I mean, they are compressed, right? They are compressing certain things here. So we should start with 32, 80, E0, etc. So, okay, don't talk. So now we're going in this function. Okay, yeah, that's right here. Let's follow along with the code here. Okay, we did this, we did this. Now we're pointing at 5d. We're doing decode temp buffer, right? And now, yeah, here we are. So we're loading our temp area pointer. That's fine. Okay, yeah, that was the checking whether we are at the end here. That's irrelevant. We're jumping to 5a12 to start with the thing, and then we're loading 5d, the first byte in our thing, which is 32. Okay, that's the new compressed data, 32, and we are taking the the top nibble, which is 30. So that should follow the thing here, though. That's good. So we have this 30 check here, right? So we take the top nibble, 30 hex. That's not 0. That's good. It's not going to be 10. It's not going to be 20. It's going to be 30. Okay, so algorithm 3, I guess. Okay, so we take this jump. That shouldn't be any different then. Meaning the 2 first values should be correct that we put out. Oh, no, the first 8 values, because we are doing 2 values per iteration for 4 times. Okay, so 5a50, I'm thinking that's just a function that does the thing, the writing. And we do that 4 times. Okay. Okay, and we're reading the next byte now. Okay, so the first one wasn't interesting because that was also the 30 thing. Now it's 80. Okay, so now it's different. Okay. Wait, what? 5d5f? Oh yeah, no, that was the value. Okay, that was the value byte. Okay, so E0. Okay, sure. Yeah, this was the meta and this was the value byte. So I'm assuming that we wrote either 80, 81 or something. Yeah, 80 and 81 was probably written out, and then E0. I mean, we can verify that, of course, if we go look at our temporary buffer here. No, that's definitely not. Okay, something happened there because there's no 80 inside. That's a bit weird, but sure. Okay, never mind. We're at E0 now. So we take the top nibble, which is still E0. It's not 0. Compared to 10, no. To 20, no. And to 30, also no. Okay. So that means that I have to add these other options as well, because we have to fall through. And now we have the else, and we're in the else part of it. Okay, and then we load the next byte. Wait, no, we load it again. because we're still pointing at 5D5F. Okay, so we're loading it and we're putting that into HL. E1F8, that's the target pointer, right? E1F8. Yeah, that's this guy here. Yeah, we did something weird here. Even though it's algorithm 3, we apparently did something completely different. That's a bit strange. Because there's no, I think we implemented this completely, right? That's very strange. So we have to look at that again though, because that doesn't make sense. Okay. So we're loading the first byte into the first output byte. Fine. E0. Okay, and we're increasing EL to the next byte, as well as the target pointer. Or no, the other way around, sure. 5D60 and this guy here. Oh, and we're jumping back. Oh, so that's all it does. 5A08 is what we jump to. That's the start of the thing. Okay, that's quite easy then, I guess. That just sets this to value 1 being this. I think that's it, right? Yeah, it just puts the value into the 10 buffer, which is this one, the E0. I mean, I'm going to try it, but it's going to be mixed up, of course. I can't really see what's going on. Yeah, I can't really, well, I mean, I can see what I'm writing, of course. And let's just do that for y is 1 and x is 0. I just want this specific chunk. So so we're loading that correct byte from the start, right? Okay, that's incorrect. And we're not hitting the function, so maybe my indexing here is incorrect as well. Room chunk index plus plus. Okay, yeah, that hasn't been updated, of course. So maybe I have to index that as well. So yeah, I think I can do that, right? Room chunk index. So room data, what was that again? That's 16-byte pointers, 16-bit pointers. So room data is actually the chunks. That's not the... Yeah, those are chunks, right? Yeah, because we're indexing by room chunk. So actually this is room chunk data, of which there are 20. Oh no, but oh, no. We are indexing that. Okay, sure. And that should be indexed from 0 to 20, correct? Yeah. So let's just, that can be, that's simply I times the width is 4 plus x, right? Yeah. Because that resets for every room. Okay, so we're indeed in, so this is room 1, 2, 3, so it's column 1, 2, 3, 4, and then we're indeed in the next row on the position is at least correct, but the values aren't. And it looks like we are either in these guys, or in these guys. So let's write them out, and then top nibble fall through. Let's see if we end up always in the 3 or in nothing, or okay, 3 1 2. Okay, there's no fall through. Oh, because okay, now we're it's because of the less than equals 0, right? That's a problem. Huh. I mean it might be, what if we change it to equals, like it's comparing and it checks the 0 flag, right? So maybe it's as easy as that. Yeah, now we do have fall through. So top nibble is 30 for the first one, and then we fall through. And then we're writing 7. That's incorrect, so... And we're not even writing 7. At least we're not hitting the 20s and the 10s though, so those can't mess us up. It's only the 30s and the fall through that happens. So it should be writing. So where should this write? This is the second thing, right? So this, so it should be this byte. Yeah. Wait, no, the index is incorrect as well. So we had this one, and then this one, and this one for the first thing. Yeah, the output position is incorrect. That's this guy here. Oh, is it? Wait, is it 16? So y and 1, let's think here. We have to write this. So this is column 1, 2, 3, and 4, and then column 1 again. So 1, 2, 3, 4. So we are dealing with this guy. We're in row 2, as in 0 base to 0 1, column 0. That's this guy. Oh no, that is correct then. Wait, is it? Oh no, I forgot. There's 4 lines in a chunk. Okay, there's 4 lines in a chunk. Yeah, this is all top. Yeah, these are the first 4 lines in the first thing, then the 4 lines. Yeah, so we have to be here. Yeah. Okay, so we have to add the length of the thing, so it's 4 times as much. But that's the 32 though. So for the second row, that's 1. So 1 times 32, which is 4 chunks down, plus x times 8. Okay, no, wait, let me do, instead of this, let's just go a little bit less. Instead of doing 5, let's do 2 rows here. Yeah. So it should start here, right? We have 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's incorrect as well then. Yeah, my offset is incorrect, or my calculation for this output offset is incorrect. Let me do 1. That should give us simply the first chunk of data. Yeah. So if it's 1, it's correct for sure. So the next one, the next row should start here. Right. So it is outputting the first one correctly, but it's overwriting. I mean, this isn't difficult though. Why am I having so much trouble with this? So y becomes 1, and we have to add. Well, first let's think of this one, right? So let's assume we are in the first row. Then that becomes 0. So we are just adding x times 8. X being the column. So if we're in column 0, we add nothing. If we are column 1, we add 8. Right, then we end up here. That makes sense. And then column 3 and column 4. Yes. And then y always adds 32. Yeah, that's to get to the from here to here. Yeah. That's that 32. But now we have to add. Oh no, it's I. It's I. And then we have to add I times this entire chunk. That's 64, right? Is that correct? No. Is the first one still correct? I think it will be. No, it's too much. Oh, I times 32, I equals. So I increments over or loops over our things within the chunk, which is this. And for the next one, we have to go to this one. That is plus 32 though. This one plus 32 is this one. We have 4 rows. Oh wait, this 1, 2, 3, 4, right. So this fills up the first chunk. Right. So yeah, that's the. No, that's 4 columns worth of, like that's the entire top row, right? Yeah. Okay, we're doing everything once except the chunk itself. Why is it dumping more than 4? 1, 2, 3, 4, 5, 6, 7. Oh, because I'm using I. Wait, so if I set it back to Y, is it then correct? Yes. But that's not correct though. Right, because that's 0. Yeah, that's 0. So this doesn't get taken into account. And then I'm doing that 4 times. Oh, am I overriding it 4 times? Wait. I'm overwriting it 4 times in the same position, right? If I offset that by 8, that doesn't make sense though, but because it's the wrong, I think it's the other way around, but that's not going to give me the correct result. Yeah, no. Wait, I times 8. Yeah, that is correct though, because I is offset. No, this should be 32 apart, right? These should be 32 apart, and that is within one chunk. So my addition should be 32 over the i's. Yeah, that's incorrect. How is that possible? What am I not seeing here? So we have y is on 0 and x is on 0, right? So we're at 0, 0 in both x and y. So we're talking about the first chunk at the top left corner. We need to, so I mean, this is going to be 0, right? Yes. Okay, let's see if I didn't make any stupid mistake here. We're writing to output at this output buffer index. And the output buffer index is an offset to which we add I plus 30j. Oh, okay, wait. What are we doing here? Yeah, that's why we're seeing wrong stuff here. So I need to give the starting point like this. I need to give this pointer or this index, and then the next one for the next chunk, I think. Yes, because the 32 happens here. This will... Yeah, this takes the buffer and puts it in the correct place, right? Yeah. I think I'm incorporating too much here. Why am I doing this 4 times? I think I'm mistaken here. I think I don't need to do this because that already happens in the output function. Yes, I think so. If I do this and yeah, so x has to be multiplied by 8 to go to the next thing here, to go to this one. And then y has to be separated by 64 for an entire thing here. Okay, so that's the first one. That looks to be correct. And then let's do the second one as well. Oops. No, we're still overwriting. So where is my top position? So if y is 1, that adds 64 to the starting position. And that's correct, right? We have 8 times 8. Wait, was it 8 times 8? Wait, let's go back to 1. We have 1, 2, 3, 4, 5, 6, 7, 8. 8 times 16, right? That's not 64. Yeah, of course, that's 128, not 64. Okay, that took a while, but yes, now it's positioning it at least here, even though the value is wrong. Yes, that's what I wanted. Okay, yeah, so this loop was already for the chunk, but we're doing that with the X. That's the same as the X thing here, that's why I was confused. Right, so we have fall throughs. Yeah, let's do let's set Y to 1, and then let's only do the leftmost thing. Yeah, so we're doing the correct one here. That's this one. Well, I mean, only this bottom left quadrant, and we have we have the first fall through, and we're writing 7. But the crazy part is oh yeah, it's a 7 we see here. Oh, okay, I didn't see that. Okay, so we do write a 7 at some point, right? Because the first top nibble 30 is going to be this entire line, which is incorrect, and we indeed see a +1, -1, +1, -1, which I assumed was correct, but apparently it isn't. Because if we look at the output here, well, which we haven't written yet. It was what, E600 or something? Yeah, E600, and then we should start at E680, which is E3 4D for EC3, so it's completely different, right? And then what we should have written was E0 instead of 07. So there we made a mistake. Let's look at our algorithm again. Right, so we are falling through here, and we are writing 7. And the value is just the level data index thing at level level data. So why is that wrong? So I'm gonna get the big thing here. It was 5A1F, and then we're falling through 5A1F, and we're falling through. So this jump is not taken, and we're in this piece of code, and it's only this. So we're loading DE into A, we're loading A into HL. So we're literally loading the value and putting it into the output array. How can that be wrong? So that means that the value I'm fetching is incorrect, meaning that's the value of DE. So DE is pointing to the wrong thing. Oh, right, I already know. It's going to have to point to the next one. So value, yeah, that needs to be one farther down. Because if we look, or no, I already incremented and I shouldn't have, I think. So where is this data? Wait, what data are we looking at again? I can't remember the address. Wait, where are we? Again, let's start from the scratch here because I forgot. Encoded tile data of scene 11 is at 5C40. Okay, 5C40 is our data exactly. So yeah, we're dealing with, well, 4 times this, then, oh no, it was 31, right? In this array, 31, that's 5B65 plus 31 times 2 equals 5BC7. That is 5D. right? And that is 5D, 5D. Well, it was a pointer. Okay, 5D, 5D is where we were at. Right, that's this one. 6E31. Oh no, that's 5C, 5D, 5D, 5D. Wait, what? 5D, 5D is here. 3280, right. 3280, so we did the 32. Oh no. Oh yeah, 3280 is the first line, which we, yeah, of course. That's the 30 algorithm, which we failed because that's this line here, and that's incorrect, right? So 3280, that would imply that, I mean, it's not 31, right? So we had 30 and 31 we've encountered, but now it's 32, so that probably does something different, because if you look at the output, that is definitely not 87F, it's like E34D, right? So there's definitely something else going on, but then the E0 is simply copied. Right, and that's where my 7 comes from. That's the next byte, and that shouldn't be the case. It should be the E0, right? Because we are writing E0 here, right? Which is 32 below our starting point, right? So I'm incrementing where I shouldn't. Yeah, this one, so I'm incrementing here. I mean, this increment happens from the previous thing here, though. So that makes it a bit more difficult now, because sometimes I have to increment. So value 1 plus delta. Is there a decrement in the code, perhaps, that I'm not seeing? Wait, no, I was looking at the code in this one here. Yeah, no, it just takes the value, right? So this is the fall through. Yeah, no. So yeah, we're taking the bottom 7 bits. Oh no, the top nibble, and that's the comparison with 10, 20, and 30. We're falling through, but we're immediately loading DE again. So that's the virgin byte, so to say, that hasn't been touched, which is 30. No, which is it was 8 E0, right? That's this one here, E0. So it's the one before the comparison. So top nibble, it's meta, it's this one, right? It's not value. I shouldn't read. Yeah, no. Yeah, of course, I shouldn't read this one. I should right, because I've already read it here, and I've incremented the level data index as well. That's why it's double. Okay, so it should be just meta. And I should increment it too, though, because we've processed this byte, of course, right? So that should make it E0 at least. Not this one. Yeah. Okay, E0. So it handles 1 byte. That's a simple 1 byte copy is a fall through. Let's go back to the first byte, though. I'm interested in this E34D stuff, because that doesn't make sense. It has something to do with the +1, -1. I'll have to unfurl that again, because yeah, we'll have to investigate the 30 thing again, which is here. This one, 5A43. So let's look at this. Okay, that's all. So everything is going to be in 5A50. That's going to contain whatever we want. Okay, so that's this one. And wait, what? So our comparison to 30 happens here. It is 0 for all these guys. So we do take the jump to 5A43. And that only calls 5A50. Oh yeah, there's there's a bottom nibble. Wait, what? Wait. Bottom nibble. Okay, bottom nibble, and yeah, that's OXOF. And then we determine whether it's. Oh yeah, we're doing two conditional jumps, right? So we're taking a bottom nibble. If it's 0, we jump to 5B29. Otherwise, we jump. So we're doing the decrement, and otherwise, we do 5B29. Yeah, increment, and we jump back, right? So we're loading DE. Yeah, how is that not the same? 5B31, so we go back to 5B31. And that's where we write out, yes. That's so weird. Okay, I'm gonna have to look at the values then while it's running, because that's super weird. I'm gonna need to stop at this point. Wait, no, how can I go there easily? I'll have to reset anyway. Okay, decode level data. Okay, let's start there again. Yeah, I did skip this function multiple times until we're at the right pointer. So once we start writing at E680, I think is what we have to do. Okay. Okay, let's see, where does it get called? So 20 times. Then the first stop things. Okay, so the call is 9db2. Right, that's 9db2. Yeah, that has to be 9db6. That's the one. Yeah, we're looking for 9db6 here. 4, 5, 6. Okay, now we go in. So now we're at on the second row, first column, and we go into here, and we're going to encounter. Yeah, we have to go here, and then we encounter the OX30 thing, because the first byte we load is going to be 32. Okay, it's offsetting my mouse pointer for some reason, and this window is stuck. Like, yeah, it's this 32 here. 3280 is what we're handling. Okay, that's irrelevant. We're jumping, we're loading DE, so we're loading 32. We're taking the top nibble, which is 30, and then we're going to the 30 section here. So we're jumping to 5A43. And the next byte is hex 80, right? Let's remember that. Okay, and then we're calling 5A50 as we saw. We go in there, we're loading the value again, which is 32. We're increasing and we're loading 80. Oh wait, we're loading 32, not the ANDed one. Wait. That might be my mistake here. So bottom nibble and. So that's meta, and then. So we're loading the 80 here. The 32 is in meta at this point. What do we do with that? Oh yeah, now we're taking the bottom nibble. Yeah, of course. That's the bottom nibble is taken from meta. Okay, sure. So we're reloading that, and that becomes 2 now instead of 1. That might be the delta 2 though. So it's not 0. That's good. Okay. We're not jumping away. So we're decrementing. Okay. Right. In the previous one, where it was 31, that became, so the bottom nibble would be 1, and then we're decrementing, and then we would jump away. Right, and now we don't jump away. So 5B to E, did we jump to that? Yes. I think so, because that's the... Yep, that's the delta of minus. That's this guy here. That's this minus thing. Right. And then writing out 4 bytes, alternating plus minus. So now we don't wait. So 2 becomes a 1, and it's not 0. So we don't jump away. So then we decrement again. Becomes 0. Okay, I don't think we've been in this thing here though. Okay, I'm gonna have to look at this because this is completely different. Now, how did we end up? Oh, right. Right, so assuming we've started with 30 hex, right? So we had 30 and 31, and now we have 32. For 30, we would take the bottom nibble. That would be checked for 0, and we jump. That's the +1, and this is the -1. Yeah, that's +1, and then the -1. Because if it's 0, then if it's 30, we jump immediately away. If it's 31, we decrement and we check for 0, and then we jump away. But it was 2, and that became 1, and then became 0. So now we are in this thing here. So wait, I'm going to do that in code here. Yeah, it's this comparison. That should become if bottom nibble equals 0, as it was before, right? Delta equals +1, and as if bottom nibble equals 1. I guess I don't have to do the decrements. I can just do or compare with a higher number, right? And then we are in the else case. That's where we are now, because bottom nibble is not 0 or 1. Bottom nibble is 2 in this case. And then, okay, we do a lot of complex stuff here, because we're indexing into another pointer here to make it easy, I guess. Yeah, because we're looping and we're returning here. So we're loading the remainder. Oh no, no. Okay, so we're loading 0 into B. That's fine. Well, I mean, that's only 0 if it's 32, right? Because we do 2 decrements, so 32 becomes 30. If, of course, we encounter a value of 33 or whatever, then that will still be a value that we need. Maybe needed equals bottom nibble -2. That I don't know if we're going to use that, but that is what happens here, right? We're saving that into B, and B is of course used as a for loop iteration count, which we have here though. And so we have to see, do we load? And yeah, we load 8 into B, so it's probably not needed. So then we load the value of DE into A. DE currently points to 5D 5E, which is 5D 5E. I mean, I can't point anymore because this window broke. That's hex 80, so that's the value byte, okay? So we do have a value byte. Okay, but we do that for every case though. So I mean, I'm gonna leave this alone now. Maybe maybe we manipulate the byte though. That's fine. We might have to do that higher up so I have access to it. But let's see what we do with it. Yeah, so we're loading that into A. So that's loading of the level of the 80. We're saving that to C, and then we're loading 5A79 into DE. So we're indexing something into DE, okay? And so we're loading B again, which contains our 2, or our 0, as it were. Yes, 0. And we're doubling that. Okay, so it is indexing because, yeah. So we're doubling that 4 times. And then we're offsetting that in 5A79. So we have another pointer, because why not? At 5A79. Okay, this window is broken too, I think. Maybe, no, 5A79. Also contains data. And we're indexing that, but it's 0, so that will not be, that will be right, literally E5 or E3, E5 if it's yeah, and those were the values, I think, right, that were referenced, or that were put into the output. So we are doubling that to 8 times, I guess, right? Oh no, four times. Meaning we have, so this one, yeah, that's 8 bytes. That's an offset of 8, right? So we have a line of 8 pre-made here, I think. Yes. Yeah, we're indexing chunks of 8 bytes here, and that's going to be the complete line, or what? So yeah, we're loading this B. Yeah, okay, we're indexing in this array. For now, it's 0, so we're dealing with the first 8 bytes, and then we're going to loop for 8 bytes, so we're probably going to copy those over. So let's see. So I'm doing this ends up with nothing. So A is 0, of course, and D is 5A79, which is this guy here. Yeah, that didn't change. And then, so we're adding that to DE, that doesn't change. And then we're looping something 5 times. And then we're loading the byte. Oh, we're loading it and incrementing it. Okay, sure. Oh, no, we're incrementing DE. Okay, we're going to the next byte. Okay, and we are rotating left C. C contains hex 80. That's the value byte, right? And we're rotating that left, so that's hex 80. Rotate left. I mean, this is shift left, so that's not good. But that won't matter because there's no overflow, so that becomes 1010. So yeah, that's rotate. Wait, how many times? Rotate left 1 times. Yeah, that becomes. No, that's decimal. Hex 80. Oh no, hex 80 is of course the top bit, and that becomes 1 then, I guess, the bottom bit. So we're incrementing the E, that's fine. C got rotated left, meaning, and that gets set in, so the top bit of 08 gets rotated left into the carry bit, right? So that's why we're checking the carry bit. So we're jumping if the carry bit isn't set, but it is set now, right? Because of that, so I'm gonna have to figure out how to do that. And then we're loading DE into A. That's the next byte of this guy, that's E3. Yep, increasing the E, so I'm going to the next one. We're looking at 4D now. Okay, and so we're writing that into our target area. E1, F0, Okay, that's our working area here. And that gets written. That's E3. And then, okay, we're going to the next byte, and then we're looping. So we're loading a byte, and this is what gets written. Then we're loading this byte, 4D. Okay, we're incrementing, that's fine. And then we're rotating left, C, which is now 0. Right, because the bit got shifted into the carry flag. Wait, okay, I didn't take a look at C before we jumped, but fine. So do we take the jump now? Yes, we do. 5A73. Oh, so we don't write out the or load the next byte, I guess. FA7C. Yeah, we're skipping this one for some reason, and then we're pointing this one. Okay, this is super complex though. I don't know why they did it so complex. A into HL, and so we're writing 4D now. Okay. Okay, C is 1 now. Okay, so that happens, okay, every 8th time it happens, right? Because we are rotating left every time. And once the top bit is set, that gets shifted into the carry flag, and then that's true. So this is going to be jumped over 8 times. Right. That does make sense. Right. Yeah, we're skipping that every time. But the weird part is what's with this, right? Why are we like copying something from here and then not all the time, but like sometimes skipping? Like, that's very weird. It would make sense if we looked at, or more sense, I guess, if we looked at the actual values or the actual tiles that are represented here. So E3 like is 2 to 7. Okay, that's still part of the wall. I guess maybe they did something like an optimization for those wall things that wait, how to explain my thinking here. Like these things here, that comes back, that returns in pretty much all the rounds here, in all the rooms. Yeah. So they optimize. They like created that as a they saved that data like probably somewhere special, because you can see it's always this. It's the same at a, well, it's not the same exactly, but it does repeat for a big chunk, like from this point onwards. It repeats, I think. Yeah. So it would make sense that they would save that separately. Yeah, let's see if the other room also has that. Yeah. This is also quite similar. I mean, it changes a bit. I guess they that's why they perhaps introduced some variation here, but I'm assuming this is this array here, this extra bit of data, this extra pointer array or data array probably contains data specific for these adornments on the wall, right? Yeah, so because they would have to store that for every room, and it's just, yeah, it's easier to just have that, to have a base set of data and have like a modifier that changes it slightly. Yeah. All right. I'm getting hungry though, so that's going to be it for today. If you want to see the next stream, it's probably not going to be tomorrow, but one of the following days, perhaps Wednesday. I'll have to check. I don't know. But thanks for watching at least, and I hope to see you next time. Bye bye.